Okay, chapter 6, section 2, the binomial probability distribution. Okay, before I dive into the binomial probability distribution, let's do a quick little recap of everything we learned in section 6.1. I think it's kind of easy to get lost in the midst of the whole thing. Okay, so in 6.1, we were first introduced to random variables, right? So remember that a random variable is a numerical value, a numerical measure of the outcome of a probability experiment, right? So the classic example presented is about flipping coins. So let's say that you have a coin and you're going to flip it 3 times, and you're going to count how many times you get a tails, for instance. So when you flip a coin 3 times, you can get the tail 0 times, or maybe 1 out of the 3 is tails, or maybe 2 out of the 3 is tails, or maybe all 3 times you get tails. Those are the possible outcomes that can happen. Okay, but all of that is driven by probability and chance, right? There are within the world of random variables, right? So we have random variables, and within that large umbrella of random variables, we have two general types of random variables that we're going to be working with. One of them is continuous random variables. We will work on that in chapter 7 and beyond. Right, so not now. The other type is discrete. Discrete random variables. Discrete random variables are situations where the outcomes have a countable number of possible results, such as in flipping the coin. If we flip one coin 3 times and we count how many times we get tails, then the number of possible outcomes is finite and countable, so it's a discrete random variable. Good. Okay, so in section 6.1, we explored that a little bit more. We thought about probability distributions. So remember, a probability distribution of a discrete random variable x provides the possible values of the random variable and their corresponding probabilities. So it's like a little cheat sheet, right? You have some sort of situation. Maybe you're flipping coins, or maybe you're rolling 2 dice and you're going to multiply the results of your 2 6-sided dice, right? So each die can land on a value between 1 to 6. You have 2 of them, you roll them, whatever values you get, you multiply them together, and you're going to analyze the situation. So you think about all possible outcomes that can happen from your experiment, and then you assign probabilities to them. That's a probability distribution, table. Good. Okay, in order for us to have a proper probability distribution, we have to make sure we adhere to a couple of rules. One of them is that each individual probability has to be a value between 0 and 1. Remember, we can't have negative probabilities, and we cannot have a probability above 100%. And the summation of all the probabilities in your probability distribution has to add up to exactly 100%, so exactly to 1, if you're using the decimal approximation, the decimal value of a probability. Good. Okay. Then in 6.1, we also looked at a formula for the mean and a formula for the standard deviation of a discrete random variable. Those formulas are valid for any discrete random variable. But what we're going to do here is look at one specific type of discrete random variable, and that's binomial. So within the larger umbrella of all discrete random variables, there exists a unique, special little subset that is a binomial. There are several other ones that are also unique little cases that fall under the larger umbrella of discrete random variables. But for the purposes of this class, we're only going to focus on binomials. So we're not going to study any of the other ones. There just isn't enough time. The world of statistics is huge, and we just don't have enough time to cover every little thing. But there's also negative binomials out there. There's Poisson distributions, and there's others out there. But we are not going to study any of those in our class. In our class, we just have 2 things we're going to focus on: the generic type. That's this larger umbrella of all discrete random variables. And then a little subset of that, some special ones, which are binomial distributions. So binomial distribution, as we'll see in a second, has its own set of criteria, some conditions that qualify the experiment as a binomial experiment. And if we are working with a binomial experiment, then we see that some special situations happen and some formulas apply. So the formulas that applied for the larger discrete one that we learned in 6.1 still apply to binomial, but we will see that we get some nice shortcuts that can happen when we identify that it's a binomial. And therefore, we can answer some really complicated situations quite easily by knowing that the binomial and knowing the formulas and also knowing how to use our calculator to solve those things. Okay, so let's move on then. So what exactly is a binomial distribution? Well, in this section, we're going to learn, here are our objectives. We're going to determine whether a probability experiment is a binomial or not a binomial. So we can learn the criteria that qualifies a situation as being something that is binomial. 2, we're going to compute probabilities of binomial experiments. 3, we're going to compute the mean and standard deviation of a binomial random variable. And 4, we're going to graph binomial probability distributions. Okay, objective number 1, determine whether a probability experiment is a binomial experiment. Okay, binomial probability distribution is a discrete probability distribution that describes probabilities for experiments in which there are two mutually exclusive disjoint outcomes. These two outcomes are generally referred to as success and failure. Experiments in which only two outcomes are possible are referred to as binomial experiments. Okay, so we're looking at a situation where there's only going to be two outcomes. As an example, it could be that you're going to shoot a free throw and you either make the free throw or you don't make the free throw. Or you're going to flip a coin and it's either heads or it's not heads. Or you're going to roll a die, a six-sided die, and it's either even or it's odd, right? So there's only two outcomes that you're focusing on. Maybe you decide to take a survey, you randomly stop people, and you just ask them a question for which there's either a yes or a no. For example, do you have any children? Yes or no, right? Yes, no, there's no in between. Or maybe you can stop a random person and ask them, were you born in California, yes or no? Right, so you have to be careful about how you phrase the question in order to make sure that there's only two possible outcomes. If you stop people and you ask them, where were you born? Whoa, there's a lot of possible answers there, right? But if you rephrase it, specifically ask, were you born in California, yes or no? Well, now you have a situation where there's only two possible outcomes. Okay, so language, we like to refer to one of them as success and one of them as failure, right? So success is usually the thing we're looking for and tracking, right? So if we're flipping coins and we're counting how many times you get a tails, we'll call tails a success because that's what we're looking for. But, if you're shooting a free throw, it kind of makes sense that making it is a success, and that's usually what you're looking for. Okay, but let's look at the full set of conditions for a probability distribution. So criteria for a binomial probability experiment. So an experiment is said to be a binomial experiment if the following four conditions are satisfied. Number 1, the experiment is performed a fixed number of times. Each repetition of the experiment is called a trial. So for example, sticking to the free throws, if you say, we're going to do an experiment, I'm going to shoot 2 free throws, and I'm going to track how often I make it. So you can keep track of that. You're only shooting twice. So the random variable x in this situation would be how many times did you make it, right? Out of the 2 times that you were shooting. So either you make it 0 times, or you make it once, or you make it twice, and that's it. Those are the only possible outcomes, and it's a fixed number of times. How do we ruin that? Let's say the experiment was a little bit different. Let's say that what I'm going to do is I'm going to take a person, I'm going to have them shoot free throws, and I'm going to count how many times they fail before they make it the first time. So, in other words, how many attempts did it take to make the first shot? That fails to be that fails this criteria of a binomial probability experiment, right? So, what could happen in a situation like that? Maybe the person walks up, shoots it, makes it. So they only did it in one shot. Or maybe they walk up and they shoot and they miss, and they shoot and they miss, and they shoot and they miss. Maybe the fourth time they finally make it, right? And then you keep going like that. But in a situation like that, we don't have a fixed number of trials. You're just letting people shoot as often as they need to until they finally make it. And in theory, there could be somebody that just never makes it. They keep attempting and shooting and shooting and shooting, and hundreds and thousands of times go by and they never make it, right? So that would fail to be a binomial experiment. That's something else. It's still a discrete probability experiment, but it's not a binomial probability experiment. Okay, next one. The trials are independent. This means that the outcome of one trial does not affect the outcome of the other trial. Okay, so once you flip a coin and you're checking to see if it's heads, you flip it, and maybe it's heads, maybe it's not, and then you flip it a second time. The second flip doesn't care what happened the first flip, right? Those two are independent of each other, right? Those are that's what qualifies as independent trials. What would break that? What situation would violate that? Let's say that you have a big hat and you put in there red balls and blue balls. Let's say you put 10 red balls, 10 blue balls, and you're reaching in there and you're pulling out the little balls, and you're just counting. Say you pull out 5 balls, right? There's a total of 20 in there, and you pull out 5, and you're just going to count how many blue balls did you pull out of there, out of the 5. And there's no repetition. So you pull one out and it's red, and then you leave it out, and then you reach in there and you pull another one out, and you don't put them back. So in a situation like that, it becomes a conditional probability, right? The probability that the third ball is a blue one is dependent on what did you do the first 2 times. How many red and blue balls remain in the hat the third time or the fourth time or the fifth time, right? So that's a situation where the trials would not be independent. Okay, but for binomial, it has to be a case where the trials are all independent. The third time you repeat this, there is the probabilities don't care what happened in the prior trials. Okay, for each trial, there are 2 mutually exclusive or disjoint outcomes, which we often refer to as success or failure, right? So we have to be careful that the situation is either you make it or you miss it. It's either top or bottom. It's either a yes or a no, right? You cannot look at a situation where there are 3 possible outcomes or more, right? We can't have ambiguity. It's either yes, no, success, failure, you made it, you didn't make it, it turned on, it was off, right? So just 2 possible outcomes that are mutually exclusive from each other, right? No overlap. What could fail that? For example, typically we have a 2-party system in this country, right? So we have Democrats and Republicans. If you stop people in the street and you random survey and you ask them, are you a Republican or are you a Democrat? And you're kind of attempting to do that, the way you phrase it might make it might qualify under this condition, or it might fail. So, for example, if I simply ask a yes or no question, such as, are you a registered Republican? Yes or no. Okay, that's mutually exclusive. Everyone will answer yes, I am, or no, I'm not. There's no ambiguity about that because I asked if you are a registered Republican. If instead you simply ask, what party do you belong to? Well, they might say Republican, they might say Democrat, they might say Green, they might say Independent. There's a variety of things. They might say they don't participate in any party at all, right? So then you're leaving the door open to lots of possible answers, and that would fail this. But if you simply rephrase the question in a way that only gives you a yes or no, then you will have satisfied this condition. Good. Okay, and finally, the probability of success is fixed for each trial of the experiment. So it doesn't change as you progress from trial to trial. The probability of success stays fixed and constant throughout. The little example I gave about the hat with some red balls and blue balls in there, that's an example where the probability is not fixed, right? Because I am not replacing it, and so therefore it fails that. Now, if you were replacing it, if you were you had a hat and you had 10 red balls, 10 blue balls, and you were reached in there, you picked one out and you noted the color, and then you put it back in there and you shook it up, and then you reached back in there and pulled one out. Now you'd have a situation that would satisfy binomial, right? In a situation like that, because you're putting it back, then the probability stays constant from trial to trial to trial. All right, so let the random variable capital X be the number of successes in lowercase n trials of a binomial experiment. Then X is called the binomial random variable. So it's customary for random variables for us to use capital letters like this to represent the random variable. And then lowercase x would represent a particular instance of that random variable. You'll see the notation in a little bit. Notation used in binomial probability distributions. There are n independent trials of the experiment. Usually we let the letter P, so let P denote the probability of success, right, for each trial, so that 1 minus P is the probability of failure for each trial. The probability of success is equal to P, and the probability of failure is equal to 1 minus P. Notice that they have to be complements of each other. And then also often we use the letter Q to represent the probability of failure. Okay, let capital X denote the number of successes in n independent trials of the experiment. And so now we let lowercase x represent a particular instance of those tries. So x is going to represent some value between 0 all the way up to n, inclusive of the endpoints. Okay, let's work on identifying some situations that would qualify as binomial experiments or identifying why they would fail to be binomial experiments. So determine which of the following probability experiments qualify as a binomial experiment. For those that are binomial experiments, identify the number of trials, probability of success, probability of failure, and the possible values of the random variable x. Okay, so let's look at the first situation. Okay, an experiment in which a basketball player who historically makes 80% of his free throws is asked to shoot 3 free throws, and the number of free throws made is recorded. Okay, this is going to be a binomial experiment because all 4 of the conditions are satisfied to guarantee that this is a binomial distribution. So number 1, there are 3 trials, right? There are a fixed number of trials as the first condition, and yep, you're only going to shoot it 3 times. If this was a situation where there was no limit on the number of times you can throw it, then that would be different. So maybe it's an experiment where you just figure out in a 1 minute, you put 1 minute on the clock and you figure out how many free throws you can make in that. Well, there isn't a fixed number, right? It could be that he makes 3, makes 7, 20, who knows how much you make in 1 minute, right? But it's not a fixed number. But this case is fixed. There are only going to be 3 free throws. It satisfies that condition. The trials are independent, right? He shoots it the first time, he either makes it or he doesn't make it. The second time, it doesn't matter whether he made it the first time or not. Assuming that this is a professional basketball player and he doesn't get psyched out about missing it the first or second time, you get up there and you shoot, and so the outcome of that attempt is independent of what happened in the previous times. Okay. Number 3, there are only 2 possible outcomes for each individual trial, right? You either make the free throw or you miss the free throw. So yes, this satisfies that condition. And finally, the probability of success is constant, and it is 80%, right? He historically makes 80% of his free throws, so that's the probability of success, which we call P, right? So in this case, this would be P. P equals to zero point 0.8, and the probability of missing it, the probability of failure, is therefore its complement, which would be equal to the 0.2. Okay, so the random variable x is the number of free throws made, and so x has the possibility of being any value between 0, 1, 2, or 3. Good. So the probability of success in this case is 0.80, and that's also what we refer to as P, just P equals to 0.80. The probability of failure is going to be the complement of the probability of success. This is equal to 1 minus the probability of success, right? Because either you make it or you don't make it. So they're complements of each other. And so this is going to be equal to 1 minus 0.80, which means that the probability of failure is 0.20, right? They have to add up to 100%. So this is the probability of failure. And so following the formula, probability of failure is equal to 1 minus P, which is equal to 1 minus 0.80, which gives you 0.20. And coincidentally, we also call that Q. So whether you use the formula 1 minus P or you use the letter Q, either way, it refers to the probability of failure. Good. Okay, so then the random variable capital X represents the number of free throws made when we make 3 attempts. So we would write down this, capital X there. And then lowercase x's could be these. Lowercase x could be a 0. You made it 0 times out of the 3 attempts. Or maybe x lowercase x1 means that you made 1 out of the 3 free throws. X equals to 2 means you made 2 out of the free throws. And the third one could mean that you made all 3. There's only these possible values, right? There's only 4 possible outcomes to this situation. To the right of this table, what we would like to do is figure out the probability of x, right? What is the probability that x equals to 0, for instance? What is the probability that x equals to 1, x equals to 2, x equals to 3? Good. Okay, and so that's exactly what we're going to study in this section. How do we figure these things out? How do we figure out the probability of each possible outcome of a binomial distribution? And then we'll see that there's some nice patterns and a nice formula, and we'll examine this situation in the rest of this section. Okay, but for now we're just identifying that this does qualify as a binomial distribution experiment, binomial experiment. Okay, let's try another one. Okay, according to a recent Harris poll, 28% of Americans state that chocolate is their favorite flavor of ice cream. Suppose a simple random sample of size 10 is obtained, and the number of Americans choose chocolate as their favorite ice cream flavor is recorded. Okay, does this satisfy the conditions of a binomial experiment? Is this situation a binomial experiment random variable? So remember, we gotta make sure it satisfies all 4 conditions. Is the experiment performed a fixed number of times? Are the trials independent? Are the trials mutually exclusive? And 4, is the probability of success constant, fixed, and the same for each individual trial? So the answer is yes for this one as well. So this is a binomial experiment because, number 1, there are a fixed number of trials. We're gonna take a sample of size 10, exactly 10, and we're gonna ask those 10 people if chocolate is their favorite flavor of ice cream, right? So there are only 10 possible answers that we will have, exactly 10 possible answers that we will have. Good. So first condition is satisfied. Second condition, is that the trials are independent from each other. So presumably, if you're randomly picking people, when you ask the seventh person, is chocolate your favorite flavor of ice cream? The seventh person, their answer will not depend on what the previous people answered, right? Hopefully, they're not being swayed by public opinion at this point. Ideally, they wouldn't even know what the previous people have answered, right? You just randomly stop people and you ask them privately. They don't know what other people have said. And so the trials are going to be independent of each other. Good. Number three, there are only two possible outcomes. Again, it's all about how you phrase the question. So if you ask a random person, is chocolate your favorite flavor of ice cream, yes or no? Then there's two possible outcomes. Yes, it is my favorite ice cream flavor, or no, it's not my favorite ice cream flavor. You can't have any other possible answers when you phrase it that way. Now, if you randomly stop people and said, "Excuse me, can you tell me your favorite flavor of ice cream?" Well, now that's a lot of possible answers there, right? You can still frame the experiment a little bit different, though, because you could say you ask them, what's your favorite ice cream flavor? And you record it. And then later, when you're reviewing your results, you kind of laser focus on, did the word chocolate come out of their mouth? Yes or no, right? And it could be that you accept all kinds of answers, like maybe chocolate mint is their favorite, or maybe espresso chocolate almond is their favorite, right? So the word chocolate came out. So you could rephrase it that way, right? So it's all about how you phrase the question, and do you break it down into a situation where there's only two possible outcomes? Yet maybe you force them to say yes or no, or maybe you let them free response, but then later when you're looking at the responses, you're specifically looking at the word chocolate came out of their mouth, yes or no, right? Okay, so yes, this is definitely two possible outcomes. Yes, it is their favorite ice cream, or no, it's not their favorite ice cream. And finally, the probability of success. So 28% of Americans state that. So that statement of the 28% of Americans, that refers to everyone, right? All 320 million Americans. Of those 328 million Americans, 28% of them indicated that chocolate is their favorite ice cream flavor. So as you're polling just 10 people, then that probability stays about constant, right? So the probability of success is going to be equal to 0.28, and the probability of failure is going to be its complement. Good. So the random variable x is the number of people who choose chocolate as their favorite ice cream. And so the random variable x can take on the values anywhere between 0 out of the 10 said they prefer that chocolate is their favorite, 1 out of the 10 said chocolate is their favorite, 2, 3, 4, right, all the way down to 10. So just like before, we're going to work on creating a table where we let capital X represent the value of our experiment, and so the lowercase is an instance of it. So capital X is our discrete random variable, and X lowercase can be 0. 0 out of the 10 people said that chocolate was their favorite, and then we want to figure out the probability of that. So we're going to have probability of our random variable, and actually I guess the notation would say this. Capital X can take on one of these lowercase values. So it's the probability that X equals to 0, for example, and we're going to figure that out. That's to be determined in a little bit. The random variable could also take on the value 1. Exactly 1 out of the 10 people said that chocolate was their favorite. So we're going to have to figure out this. What's the probability that exactly 1 out of the 10 people said that? Good. And so X can take on the value of 2 and 3 and 4 and so on and so forth. And then way down here is 10. Right? So the largest value it could be is that maybe all 10 of them. We asked 10 people and all 10 of them said chocolate was their favorite ice cream. So then again, we're going to have to figure out what's the probability that we get exactly 10, right? When we figure out each individual probability here and fill out this whole table here, we'll have like a little cheat sheet that lets us know the possible outcomes that can happen from this experiment of asking 10 people if chocolate is their favorite ice cream, and not just the possibilities, but then the probabilities associated with each possible outcome. Okay, and remember again the probability of success. Probability of success is equal to the letter P, or we use the letter P traditionally, and that's in this case equal to 0.28. And the probability of a failure is often we use the letter Q, and that's also 1 minus P, which is the complement, which is equal to 0.72. 0.72, right? These two have to add up to 100%, right? Because they're binomial. There's only two possible outcomes. Either they said yes or they said no, and so they add up to 100%. Okay, so let's move on. Okay, third example. A probability experiment in which 3 cards are drawn from a deck without replacement and the number of aces is recorded, right? So there's a standard deck of cards, 52 cards in there, 4 suits. Each suit has 13 cards, right? Your standard deck of cards, and you're gonna shuffle them all up, so it's all random in there, and you're gonna pull one out, flip it over, and decide, is this an ace, yes or no? You're not going to put it back, right? It's without replacement. You're not going to put it back in the deck and leave it there on the table. And you flip another card. And again, you determine, is this an ace, yes or no? And you do that a total of 3 times. Does this satisfy the conditions of a binomial situation? Is this a binomial random variable? And the answer is, no, it is not. It is not a binomial. It's not a binomial experiment because the trials are not independent from one another. Notice that with the first card, when you first flip it, the probability of getting an ace is 4 out of 52, right? There are 4 aces in the deck. So the odds of the very first card, and you flip it over, you shuffle the 52, and you flip one over, there is a 4 out of 52 chance that the first one is an ace. What about the second one? So because we are sampling without replacement, if an ace is selected on the first trial, the probability of an ace on the second trial is equal to 3 out of 51, right? Because there's already 1 ace that has been removed. The first one was an ace. So now there's only 3 left in the deck, and there's a total of 51 cards left. So the probability that the second one is an ace, given that the first one was an ace, is equal to 3 out of 51. And if an ace is not selected on the first trial, then the probability of an ace on the second trial is still 4 out of 51, right? So the likelihood that the second card is an ace will vary depending on whether an ace was pulled out of the deck the first time around. And you can see that the third time you pull a card, the odds of it being an ace or not an ace, again, will depend on what happened the first 2 times. If the first 2 cards were already aces, you can already see intuitively that it might be really, really hard to make sure that the third one's also an ace. You've already pulled out 2. There's only 2 remaining in the deck, and now you're going to pull another one, and you're hoping that it's again an ace. That seems pretty tough, right? And if we had 4 cards, what are the odds that the first one's an ace? That's pretty hard. The second one's also an ace. That's really hard. The third one's also an ace. That seems incredibly, fantastically hard. And then the fourth card is also an ace, right? That would be like beyond winning the lottery kind of odds, right? Very, very difficult for that to happen like that. Good? Okay, so this is not a situation we're going to study in this section. This does not satisfy the criteria for a binomial distribution. And in this section, we're only going to be focusing on binomial distributions. Binomial random variables. Okay, a note of caution about the language. The word success does not necessarily imply that something is positive. Success means that an outcome has occurred that corresponds with the probability P, the probability of success. That's all that means. It's in an experiment, it's the thing we're looking for. And sometimes it means that it's a success, like when you're shooting free throws, if you make it, we call that a success. Okay. So it's the thing we're counting. You could easily flip that around and just kind of count how often they miss it, and we can call missing it a success, right? So it just depends on how you're looking at it. It could be that we are testing random blood samples and we're looking to see if they match mine. I am O negative, and either they match mine, yes, or they don't match mine, no. So maybe the thing I'm looking for is when they are O negative. That's what I would call a success. Now, that doesn't mean that it's a good thing or a bad thing. It's just the thing I'm looking for. I'm counting how many people, let's say we're going to randomly stop 20 people in the streets, ask them if they would be willing to donate a blood sample, and then test it and see if their blood is, see if their blood is O negative, yes or no, right? Okay, so success doesn't necessarily mean it's a good thing. It's just the thing we're counting. Right? So keep that in mind. Okay, objective number 2, compute probabilities of binomial experiments. Okay, so let's dive into an example. Earlier, when we were trying to establish whether situations fit the conditions of a binomial distribution or not, we looked at this example. An experiment in which a basketball player who historically makes 80% of his free throws is asked to shoot 3 free throws. So we looked at this situation. We concluded that it did satisfy all 4 of the criteria of a binomial distribution, a binomial random variable. There were 3 fixed trials. Each trial is independent or approximately independent. There are 2 possible outcomes. You either make it or you miss. And the probability of success, the probability you make it, is fixed at 80%, and the probability of missing it is fixed at 20%. So this does satisfy the conditions of a binomial random variable. And the random variable x can take on one of 4 possible values. Either he makes 0 of them, or he makes 1 out of the 3, or 2 out of the 3, or he makes all 3 of them. And so we noted that we would like to create this little table where the random variable is identified as all the possible outcomes that can happen. And then this is the hard part. We want to figure out the probability of getting each one. So let's dive into this, filling out this table, figuring out each one of these. So I'm going to take this situation, but I'm going to tweak it just a little bit. Okay, so an experiment in which a basketball player. So let's be more specific. Let's not choose a basketball player. Let's choose the basketball player. Let's say that we're talking about Michael Jordan. Okay, so not just a basketball player. We're talking about M. Jordan. Michael Jordan. Okay. Who historically makes, okay, so that's not his number. Let's look him up. Okay, so just a quick little look here. Looks like he had about an 83.5% lifetime free throw average. Let's just round that to 84, just to have a nice round number, just that this doesn't come out too crazy. So for him, let's just say that this is about 84%. This is 84% instead of just the 80. So an experiment in which Michael Jordan, who historically makes 84% of his free throws, is asked to shoot 3 free throws. Shoot 3 free throws. And then the number of free throws made is recorded. Okay, so as we saw earlier, this does satisfy all the conditions of a binomial random variable. And so the random variable x can take on the values. So we're going to have this little table over here. And x can take on the values of 0. It can take on the value of 1. Right? He makes 1 out of the 3. It could take on the value of 2. He makes 2 out of the 3. Or maybe it could take on the value of 3. He makes all 3 free throws. right? So then this is going to be the probability that the random variable takes on one of these lowercase x values. So we want to figure out the probability that x takes on the value 0, the probability that x takes on the value 1, the probability that x takes on the value 2. Okay, so that's going to be our goal, to figure out each one of these probabilities. In order to figure that out, I'm going to do this whole long crazy thing. I want you to pay attention, hopefully follow along, but it's going to get messy. And keep in mind that this is not what you're going to be asked to do. So you're not going to have to recreate the craziness that I'm about to do. I'm going to do it this way so that we can identify some nice little patterns, so that we can see how we can do it in a quicker, faster, easier way, how we can establish a formula for it. And once we have a formula, it'll be very easy to do. Okay? So again, don't let this scare you off. This is not what you're going to have to do yourself. I'm just going to explore this situation and develop our formula for it. Okay, so in order to figure out each one of these individual probabilities, we need to figure out all possible outcomes that can occur when Michael Jordan attempts 3 free throws. Okay, so on the first free throw, he either makes it or he misses it, right? So we have to establish the success, right? So success for us is going to be that he makes it. Success is that he makes it. And failure is that he misses, right? So I'm just going to use the letter S and the letter F, and just to make sure, because my lowercase f's look a lot like my s's. F for failure, S for success. He makes it, he misses it. So his first attempt at the free throw, he will either make it, success, or he will miss, right? Put it down here, it's a failure. What I'm going to do is a tree diagram so we can identify all possible outcomes. So first attempt, he either makes it or he fails. Second attempt, let's put it over here. Second attempt, well, again, he either makes it or he fails. And then over here, again, he either makes it or he fails to make it. Good. And then finally, we have our third attempt. And again, either he is successful, he makes it, or he fails to make it. And then again, he either makes it or he fails to make it. And then he either makes it or he fails to make it. And he either makes it or he fails to make it. Okay, so following along this tree diagram, we see all possible outcomes that can occur when you attempt 3 free throws. So let's follow each one of these. So the first one, following the tree in this direction, here's the case where he made the first one, he made the second one, he made the third one. So this is S, S, S. Makes the first one, makes the second one, makes the third one. Good. Following the tree in this direction, he either makes the first one, then makes the second, and then fails the third one, right? So this one would be the case of S, S, F. And then in this direction over here, this would be the case of S, F, S. And then over here, this would be the case of S, F, F. He makes the first one, fails the second, fails the third. Then following over here, these are the cases where we start off with a fail. So he fails the first one, then he makes the second, makes the third one. So this is F, S, S. This is F, S, F. This is F, F, S. And then finally we have F, F, F. Okay, so we see that there are 1, 2, 3, 4, 5, 6, 7, 8 possible outcomes. 8 possible outcomes. So if you ask yourself, what's the probability that he makes all three? 1, 2, 3. It's tempting to think, well, that's this situation, 1 out of 8, right? No, it doesn't work that way. It doesn't work that way because even though that there are 8 possible outcomes, they are not all equally likely of occurring, right? The probability of success is different from the probability of failure. So some of these situations are more likely to occur than others, right? The possibility of him failing all 3 is going to be the most unlikely outcome because he's pretty good. He usually gets 84% of his free throws, so for him to miss 3 in a row is not very common. Okay, so what is the probabilities? What we have to do is go back to our chapter 5 ideas and think about the fact that this statement here, the probability that we get this situation, success in the first one, and success in the second one, and success in the third one. These are and statements. We said that they were all independent. Therefore, we know that we get to multiply them, right? This is the multiplication rule from back in chapter 5. Okay, so to figure out this probability, it's really the probability that the first attempt is equal to a success and the second attempt is equal to a success and the third attempt is equal to a success, right? So we have 3 different statements here, kind of glued together by this and they're all independent. So we know that this is going to be equivalent to the probability that the first one is equal to a success times the probability that the second one is equal to a success times the probability that the third one is also equal to a success. And they're all independent, right? So the probability that the first one's a success, that's 84%. Probability that the second one is a success is also 84%. They're all 84%. So this is just going to be equal to 0.84 times 0.84 times, once again, 0.84. Or 0.84 to the power of 3. Good. So let's just calculate that. 0.84 to the power of 3 is equal to 0.5927, or approximately 59.27%. Okay, that's the probability that this situation happens, that he makes all 3 of them. So going back up to our tree up here, I'm going to say that this top one up here, just for notation's sake, that this is the probability that we have SSS, and so that's equal to the probability of having a success, then a success, then a success. That's going to be 0.84 times 0.84 times 0.84, which equals to 0.84 to the power of 3. Good. And so we saw that that equaled 0.5927. Okay, let's look at another one. Let's jump over here to this one, FSF. Let's look at that situation down here. So now let's look at the probability that we get F, then S, then F, in that order. So probability of FSF means you fail the first time, you are successful the second time, you fail the third time. So this is going to be the probability that the first one is an F times the probability that the second one is a success times the probability that the third one is a fail. Good. So we see that the probability of failure is going to be the complement of the probability of success. The probability of success was 84, so that means that this is going to be 0.16. Probability of failing is 0.16. The probability of being a success, that's 0.14. And the probability of failing, once again, is equal to 0.16. Good. Okay, so this means that we're going to have 0.84 times 0.16 squared. Right, I'm just combining the ones that are similar. This one and this one are the same. We're multiplying everything. So this is 0.16 squared. And while we're at it, this is to the power of 1. So we have one copy of the 0.84, which is the success, and two copies of the 0.16, which was the failure. Good. So again, we can go to our calculator and figure out that result. So it's 0.84 parentheses times parentheses 0.16 to the power of 2 close parentheses, and so here we get 0.215 0.215. So a pretty small chance that this can happen. This one had a 59.27% chance that this would be the outcome, success, success, success. The outcome of having a fail, then success, then a fail, that is only about a 2.15% chance of happening, a much, much more unlikely outcome, right? But okay, going back to this tree then, connecting it here, so now we have that this is probability of FSF, which is equal to probability of failing. We said that that's equal to 0.16 times probability of success, that's 0.84, times the probability of failing again, that's 0.16. Good. And so we can regroup them just to make it nice and neat. So let's say that it's 0.84 to the power of 1 times 0.16 to the power of 2. Okay, so we can see the pattern now, and we'd have to go with the rest of them. So let me just fill out the rest of this. Okay, that looks painful. Remember, you are not going to be asked to reproduce this, so don't let this scare you off. You're not going to be asked to do anything like this. The only reason I'm doing this is so that we can look for patterns, so that we can establish a formula, so that we never have to do it this way again, right? So speaking of patterns, we see some really nice patterns appearing already. So notice that when we were trying to find the probabilities, right, we have the probability of, for example, say this one, success, success, failure. We end up with 0.84, probability of success, times 0.84, probability of success, times 0.16, probability of failure. And then when we regroup them, we get this, 0.14 squared, right, 2 successes, and then this we can raise the power of 1 failure. Say moving on to this one, probability of success, fail, fail, then that's equal to 0.14 times 0.16 times 0.16, which gives us 0.14 to the power of 1 times 0.16 to the power of 2. So do you see that what we could do is kind of skip this middle part here and simply just write down the probability of success, the probability of failure, and then we raise it to the power which represents how many times we had a success in that little outcome, and then how many times we had a failure in that little outcome, right? So I'm pointing this out. We had 1 success, therefore we have 0.84 raised to the power of 1. On the other hand, we had 2 failures, so we raised the probability of failure, 0.16 to the power of 2. Good. In another situation, let's say over here, here we had 2 successes, so we're going to have 0.84 to the power of 2, and we had 1 failure, so we're going to have 0.16 to the power of 1. Okay, so that makes it really easy to kind of skip this middle part and go from here all the way to there. Okay, likewise, the very next one here has 1 success and 2 failed, so we can kind of skip this middle part and see that we have 0.84, that's the probability of success, to the power of 1, right? 1 success, so 0.84 to the power of 1, and 2 failures, fail, so that turns into 0.16 to the power of 2. Okay, so we can easily skip this middle part by noting that all that really matters is how many successes and how many failures did you have in that particular instance, and the order in which they occurred does not matter when determining the probability of that particular outcome. Good. So just to finish the pattern out, coming back up to the top, there were 3 successes and no failures. So just to kind of complete this, we can also include 0.16 to the power of 0, since there were no failures, 3 successes. And down here, I'm going to scoot this over. Let's erase it and scoot it over. This is going to be the case where there are 3 failures and 0 successes. Good. Okay, so we have the probability of each one of these possible outcomes. And the difference, though, is that these probabilities, we can convert them into decimals and get the decimal approximation, as we did over here, for example, or as we did here. So let's focus on this one for a second. This one was FSF. That's this one right here, FSF. It equals this, and when we multiply it all out using our calculator, this turned into 0. So this one in particular translates to 0.0215, or about a 2.1% chance. This is the probability that this very specific situation happens. The probability that Michael Jordan fails the first shot, then he makes the second shot, then he fails the third shot. In this specific order, that is this probability. But that's not exactly what we were after. We wanted to fill out this table over here. So, for example, we wanted to figure out this one. What's the probability? What's the probability that he makes exactly 1? That's what this means. So the probability that x equals to 1, which is successes, this is the probability that he only has 1 success. This has no specific order, right? Whereas the probability that he has FSF, this has a specific order, a specific sequence. He fails the first one, he makes the second one, he fails the third one, right? In a specific order, right? So this is with order, and this is without order. We just want to know what's the likelihood he makes one of them, 1 out of the 3, not in a particular order. Whereas this is one case of that, but there are other cases where he might only make 1. What if he only makes the third one and misses the first 2? Or maybe he only makes the first one and misses the other 2. Okay, so we're going to use this really ugly table here to help us figure out the individual values of each one of these ones over here. Okay, so let's do that. Okay, so the probability that x equals to 0, this is the probability that he makes none of them. As we can see from our table, there's only one way that can happen. He makes 0 of them. That means he fails 3 times. This is equal to the probability that he has fail, fail, fail There's only one way to do that. And as we can see from our table, that's just going to be equal to the probability of having 0.84 to the power of 0 times. Let's put this over. And 0.16 to the power of 3 times. Good? Okay, so what's the probability that he makes exactly one of them? Right? Again, order doesn't matter here. So we have to think about all the ways that that can happen. Probability that he makes exactly one of them is equal to the probability that he... Oh, let's come back over here and spot them. Okay, so the probability he makes exactly one of them. So he makes one, fails two. Makes one and fails two. That's this one. Makes the first one, fails the other two. Or this one, he makes the middle one, fails the first and the last. Or this one, he fails the first two and he fails the last one, right? So these are all the ways in which he has exactly one success. He makes one. So coming back over here, this can be accomplished in one of three ways. Either he has an SFF situation, makes the first one, fails the second one, fails the second one. Or another way that this can be accomplished is to have an FSF situation. FSF situation, or to have an FFF, FFS. Good. Okay, we know from chapter 5 that when we see an OR statement, we know that they're addition. So this is going to be equal to having a probability of SFF plus the probability of FSF plus the probability of having FFS. Okay, well, again, following our chart here, we see that this one is going to be equal to 1 success, 2 failures, 0.84 times 0.16 to the power of 2, power of 1. And this one plus, well, again, there's going to be 2 failures, 1 success. So that's going to be 0.84 to the power of 1 and 0.16 to the power of 2 plus, finally, the last one. Again, we have 1 success, 0.84 power of 1 times 0.16 to the power of 2. Well, we can see that there's going to be 3 different terms that we add, but they're all identical. Because here the order mattered, but then when you actually calculate it and you multiply it, all that really matters is that you have 1 copy of the success, that's 0.84, times 2 copies of the failure, and that determines this one. And this one ends up being the same, and this one ends up being the same. So we know from our algebra work that means that we can combine them and say that we can just calculate it once and multiply it by 3. So if we multiply 0.84 power of 1 times 0.16 the power of 2, and then because there are 3 different ones, we multiply this by 3. Right? Okay, and that is the probability that x equals to 1. Let's figure out the probability that x equals to 2. This the probability that x equals to 2. Again, here the order doesn't matter, so we have to look at our table and figure out all the places where there were exactly 2 successes. 2 successes exactly. Okay, well this one's a 2 success situation. Here's a 2 success situation. Here is a 2 success situation, and that's it. So in those 3 cases, we have 2 successes and 1 failure. Remember, each one of these represents a specific order. So made the first one, made the second one, missed the third, made the first, missed the middle one, made the third one, right? And so these constitute this, where order doesn't matter. We just want to track how many times the case when he made it exactly twice. So this is going to be made up of the probability of having an SSF situation or having an SFS situation or having an FSS situation. Good. Again, or means that we add them. This is going to be probability of SSF plus the probability of SFS plus the probability of FSS. And so we see that for this case, there are 2 copies of the success times 1 copy of the failure, plus, again, 2 copies of the success, 1 copy of the failure. And finally, same thing, there's going to be 2 copies of the success and 1 copy of the failure. Okay. Once again, we see the situation that we have 3 things that we're adding, right? They're separated by this summation here and this summation over here. 3 things that we're adding that they're all identical. Either way, we have 0.84 to the power of 2 times 0.16 to the power of 1. Here, the order matters, but when we multiply 3 numbers, the order in which we multiply them doesn't matter. So the 3 of them are identical. So once again, we can combine this to be 3 times 0.84 to the power of 2 times 0.16 to the power of 1. Good. Okay, and finally, let's think about the probability that we get exactly 3 successes. So that would be the probability that x equals to 3. Well, there's only one way that can happen. 3 successes means he makes all 3 of them, and that would be that guy right there. So this is equal to the probability that we have SSS, which is equal to the probability of having 0.84 to the power of 3. 0.84 parentheses to the power of 3. Okay, so remember, again, let me remind you that you're not going to be asked to redo this whole crazy thing. The whole point of doing this is so that we can establish a nice pattern. And we're pretty close to being able to do that. Let's bring this information over to our table now and fill out our table. So coming back over here, actually I'm going to erase this and make it a little bit bigger so that we can have more room for writing. So I'm just going to erase this. And I'm just going to redraw it or redo it and just put a little more space. Okay, so the first case is that x equals to 0, right? Our random variable x equals to 0. And so we want the probability that x equals lowercase x. So the probability that x equals to 0. That's what we want to know. Well, we can see that there's only one way that could happen. That's this. So this is really equal to 0.14 to the power of 0. We know that any number raised to the power of 0 is going to be 1. So this really won't have effect on our answer. Really, there are 3 copies of the failure, right? 0 successes means that there were 3 fails. That's what this means. And then the next one is going to be when x equals to 1. Probability that x equals to 1. Well, that's this guy down here. We can see that this is going to end up being our result. It's going to be 3 times 0.84 power of 1 times 0.16 to the power of 2. Right? Some nice patterns are starting to show up. Probability that there's 1 success, well, that's it, 1. 0.84 is the probability of success to the power of 1. And if there's 1 success, that means that there are 2 failures. So that's why we have 0.16 to the power of 2. And this 3 right here refers to the fact that there are 3 different ways in which that particular scenario can occur when you think about specific order. One success means that it could be that you made the first one, failed the other two, or made the middle one, failed the other two, or made the last one, failed the first two. Right? These are all the possible ways in which this can occur. Good. Okay, the next one, x equals to 2, is probability that x equals to 2. And again, we see from over here that this is the pattern that occurs. We have a 3 times 0.84, the power of 2, times 0.16, the power of 1. Power of 1. One fail, 2 successes, 3 ways that that can happen. And finally, the last possible thing that can happen is that x might be equal to 3. So the probability that x equals to 3, well, we can see in this last situation over here, there's only one way that can happen. 3 successes means he made all 3. So this would be the case of 0.84 to the power of 3. And just to make the pattern complete, we're going to throw in the 0.16, the power of 0, to show that there were 0 failures, 3 successes. And again, just to make the pattern complete, I'm just going to throw in a 1 here, because there's only one way that can happen, and also a 1 up here, just to show that there's only one way that can happen. Okay, so now we can go over to our calculator and figure out each one of these, turn it into a decimal. I'm going to round to 4 significant values, and we'll have our complete probability distribution table. Okay, so finally, after all that work, we get our probability distribution table. We have all the possible outcomes when Michael Jordan shoots 3 free throws, and we're letting the random variable x represent the number of successes, the number of times he makes the free throw. So you can either make 0 of them, he can make 1 out of the 3, 2 out of the 3, or maybe he makes all 3 of them. And we see that there's a very nice pattern to be able to figure out those possible answers. And we can, multiply with our calculator and get these values. So we see that the most likely result is that he makes all 3 of them. And there is a 59% chance that'll happen. The second most likely outcome is that he makes 2 out of the 3. There are several ways in which that can be accomplished. That's why we had to do this whole crazy table to figure out all the different possible ways that can happen and use that to help us figure out the probability that he makes exactly 2 of them. Remember, this makes 2 of them, doesn't care about order. Over here, when we see F, S, S, that cares about order. So we use this to be able to figure out this. Okay, so we see that there's a 33.87% chance that he makes 2 out of the 3. There is a 6.4% chance that he makes only 1 out of the 3. And there is a 0.4096% chance that he makes none of them. Good. This is a proper probability distribution because it satisfies the 2 conditions. Each probability is between 0 and 1. And if we add these guys up, all 4 of these, they will add up to 100%. Give or take a little bit because of rounding. But they do add up to 100%, which means that we've accounted for all possible outcomes. Okay, so we're looking for patterns, right? So let's do one more, and hopefully we see the pattern really nice and neat, and then we'll jump to the formula. Okay, now let's look at one more example. According to the American Red Cross, 7% of people in the United States have blood type O negative. A simple random sample of size 4 is obtained, and the number of people X with blood type O negative is recorded. Right? So keeping track of how many of those 4 have O negative. Construct a probability distribution for the random table. For the variable x. Okay, so does it satisfy a binomial situation? Does it meet the 4 criteria? Number 1, is it the case that there is a fixed number of trials? And yes, n equals to 4 in this case, right? There's going to be 4 people, 4 blood types that we're going to test. So it's a fixed number of trials. The trials are independent. These are randomly selected people. Whether or not the first person was O negative does not affect whether or not the second person is O negative, right? So they're all independent. Um, there are two mutually exclusive outcomes, right? We're only checking yes, you are O negative, no, you are not O negative, right? So it is binomial. There's only two possible outcomes: yes, you're O negative, no, you're not O negative. And finally, the probability of success stays constant. And again, 7% of all people in the United States, all 320 million people, 7% of those 320 million people are O negative. So if we pull out 4 randomly selected people from that population, we could say that the probability of picking a person that is O negative is approximately constant, which is going to be about 7%. Right? So it does satisfy all 4 conditions. This is a situation that satisfies a binomial random variable. So let's analyze it like we did before. Okay, so in the previous case, we were shooting 3 free throws, so n was equal to 3. In this case, now we're going to have the case where n equals to 4. Right, so here n equals to 4, and the probability of success, which is p, in this case equals to 0.07, which means that the probability that we fail, probability to fail, is 1 minus the probability of success, which is equal to 1 minus p, which is equal to 1 minus 0.07, which gives you its complement, or 0.93. Right? So if the probability of success is 7%, the probability of failure is going to be 0.93. Okay, so the random variable can take on one of these values, right? So we're going to have a table where we have our random variable x can take on the value of x equals to 0. Maybe none of the 4 have O negative. Or maybe the random variable can take on the value 1, 1 out of the 4 has O negative, or the random variable can take on the value of 2, 2 out of the 4 has O negative, or the random variable can take on the value of 3, 3 out of the 4, and or finally the random variable can take on the value of 4. Okay, so based on the previous one, we can probably guess what the pattern is going to be, but once again, let's go through the hard work of determining each one of these probabilities, and then once again identifying that pattern. So the first thing we want to do is think about the tree diagram that's created so we can look at all possible outcomes. So instead of doing it by hand, I'm just going to jump to this image. Okay, so with this image here, we can see a tree diagram which features 4 different trials. So for the first trial, we either have a success, we found someone with O negative blood, or we failed. And then for the second trial, we pick a second person, and then that person is either a success or a fail, and so on and so forth. So we can go through 4 different trials, and this tree diagram will lead us to all possible outcomes. So for example, this one means the first person was successful, O negative. Second person failed, not O negative. Third person was successful, yes, O negative. And then the fourth person failed. So that leads to this little scenario of S, F, S, F, success, failure. First person was O negative, second person was not O negative, third person was O negative, fourth person was not O negative. Okay, and so we can do that for all the various outcomes, and we see that there's going to be a total of 16. 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12, 13, 14, 15, 16 possible outcomes. Remember that each one of these represents a specific order of things. What did the first person get? What did the second one? What did the third one? But when we want to create our random variable binomial distribution table, we don't really care about order. We just want to know what's the probability that 2 of the people were O negative. What's the probability that 3 were O negative? So what we're going to do is keep track of how many successes there are. So here there are 4 successes. Here, there are 3 successes. Here, there's also 3 successes. Here, we have 2 successes, 3 successes, 2 successes, 2 successes, 1 success, 3 successes, 2 successes, 2 successes, 1 success, 2 successes, 1 success, 1 success, and then finally 0 successes. Okay, so then we're going to use this one to figure out the probabilities that we're actually interested in. So let's figure them out. What's the probability that x equals to 0? Well, that one's really easy. That's just this one. Okay, so what's the probability? Probability that x equals to 0. That's the probability that there are 0 successes. Well, there's only one way that can happen. We see that right down here. There's only this way. This is the only way that there's 0 successes. Only that's the only way it can happen. So that's just going to be equal to the probability that we have a fail, and a fail, and a fail, and a fail. 4 fails, no successes. And so we know from our previous pattern that this is going to be equal to the probability of failing, which we established was equal to 93%. 0.93. Well, actually, just to keep with the pattern, make space over here. It's the probability of success, which was 0.07 times 0.93. But we know that we have 4 fails and 0 successes. And there's only one way that this can happen. Good. That's the probability that x equals to 0. Okay, what's the probability that x equals to 1? Exactly 1 success. So let's come over here and figure out all the ways in which we have exactly 1 success. Well, we see here that we highlighted this one. There's 1 success there, only 1 success there, only 1 success there, only 1 success there, and that's it. Those are the ways to do it. So let's write it down. So the probability that we get exactly 1 success is equal to the probability that we get one of those. So it could be S, F, 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 or first one was successful, the other 3 were fails, or the second one was a success, the other ones were fails, or maybe the third one was a success, the other one were fails, or maybe the first 3 were fails, the last one was a success. We see from our previous patterns that these 4 cases are going to be identical. Each one of them is going to represent 1 copy of a success and 3 copies of failure. So this is going to be equivalent to 0.07 to the power of 1 times 0.93 to the power of 3. And that would be this one right here. Plus, and now we do the next one, and this one would again be a 0.07 to the power of 1 times 0.93 to the power of 3 plus 0.07 to the power of 1 times 0.93 to the power of 2. And finally, the last one, which is going to be the same thing. It's going to be another plus 0.07 to the power of 1 times 0.93 to the power of 2. Right? So the point is we have 4. See, this one represents this. 1 success, 3 failures. And then this one is represented by this one. 1 success, 3 failures. And then this one is represented by this one. 1 success, 3 failures. Oops, that's supposed to be a 3 up here. 3 failures. And finally, the last one, this one, is represented by this one. Right? So we're adding 4 things that are identical. So instead of doing all that, what we could do is just say that the probability that x equals to 1 is going to be equal to 4 copies of 0.07 to the power of 1 times 0.93 to the power of 3. Right? Nice little patterns are starting to emerge. Good, good, good. Okay, so for the other ones, I'm just going to skip this part where we write it all out like that and just jump to the pattern that we're starting to see. What's the probability that x equals to 2? Okay, well, let's come back over here and count all the ways in which we can get exactly 2. So 2, that's this one, SSFF, or this one, SFSF, or this one, that's SFFS, or this one, that's FSSF, or this one, or this one. Okay, so that's it. So the probability that x equals to exactly 2, order doesn't matter, is equivalent to the probability of finding one of those. It's equal to the probability of SSFF. Okay, so there are 1, 2, 3, 4, 5, 6, right? And following the pattern from above, I know that each one of these is going to be identical. The probability of the first one is going to be 0.07 to the power of 2, because there's 2 successes, times 0.93 to the power of 2, again, because there's 2 failures, plus, now the next one is going to be 0.07 squared, because there are 2 successes, and 0.93 because there are 2 failures, and so on and so on and so forth, right? So I don't have to write it all out. I know that there's going to be 6 identical values that we're adding together. So we can just jump down to saying that this is going to be 6 times 0.07 squared times 0.93 squared, right? And that's the probability that x equals to 2. Now let's look at the probability that x equals to 3. Probability that x equals to 3, that there are 3 successes. Again, if we come back over here and we count them, there's a success right here. There's 3 successes, SSSF, or there's this one, or there's this one, or there's this one. That's it. There are 4 different ways in which we can have exactly 3 successes. And now just following the pattern, I know that this is just going to be 4 times 0.07 to the power of 1. Oh, sorry, power of 3. Power of 3, because there are 3 successes, times 0.93 to the power of 1. There's only 1 failure. Okay, and then finally, the last one is the probability that x equals to 4. Probability that x equals 4 is equal to 1 times 0.07 to the power of 4 successes, which means that you would have 0 failures. Good. Okay, so let's combine all that into a probability distribution table for this scenario. So we have that in this case, n equals to 4, right? There are 4 independent trials. Probability of success is equal to 0.07, also known as P, right? P equal to the probability of success is equal to 0.07, and Q, which is equal to 1 minus P, which is equal to the probability of fail, is equal to the complement, which is equal to 0.93. Okay, armed with all that, we can put together our distribution table for the random variable x, and we see that the pattern is actually really easy. Now we have a nice pattern that we can follow. So the random variable x can take on the value x equals to 0, 0 successes, and the probability that x equals to 0 is going to be equal to probability that we have 0 successes. So that's 0.07, the power of 0, 0 successes, which means that all of them were failures, 0.93 to the power of 4. And we can see there's only one way to have 0 successes. That's this last one down here. 0 successes. 0 successes. Good. And so that's why we have to have a 1 out in front. 1 times that. Good, because there's only one success. One way that can happen. 0 successes, that means all fails. Okay, so then we move on to the next one. What's the probability that x equals to 1? X equals to exactly 1. 1 success. Good. So now that's going to be the probability that x equals to 1 equals, I'm going to skip that for a second. I know that there's going to be 0.07 to the power of 1 success, and 0.93 to the power of 3. If there's only 1 success, that must mean that there are 3 failures, right? Since we have 4 trials altogether. But this doesn't care about order, and there's lots of ways that this can happen. So that's when we got to come over here and take a look at this so we can figure out all the ways that could happen. So that could happen this way, or this way, or this way, or this way. And that's it. There's 1, 2, 3, 4 different ways in which that can happen. So this, highlight it here. And that's why we have to have a 4 right here. 4 times these decimals being multiplied. Right, so we can see the pattern as we move forward then. Okay, so now let's try when x equals to 2. X equals to 2, 2 successes. It's the probability that x equals to 2 equals to, I'm going to skip that there for a second, 0.07 to the power of 2. So if there's 2 successes, that must mean that there were 2 failures as well. And again, we can come back over here and count them all. So all the ways in which we had exactly 2 successes, that's that one, and 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 that one. 1, 2, 3, 4, 5, 6. 6 different ways in which we had exactly 2 successes. So we got to multiply this by 6. Good, almost done. X equals to 3 now. So the probability that x was 3. 3 out of the 4 people had O negative blood. Skip that constant for a second, and we multiply this by 0.07 to the power of 3 times 0.93 to the power of 1. So if we had 3 successes, that means we only had 1 failure. And again, we can come back over here and count the number of ways that could have happened. So all the ways in which we had 3 successes. So that's this one, and this one, and this one, and this one. 1, 2, 3, 4 different ways that could happen. So I'm going to highlight it, and so that means that there's a 4 times there. 4 times that. Good, 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 good. Okay. And that means that this guy is this guy. And finally, the last thing that could happen is that maybe x equals to 4. All 4 of the samples resulted in O negative blood. That's the probability that x equals to 4. So skip that guy again. That means that we have 4 successes. 0.007 to the power of 4 times 0.93 to the power of 0. 0 failures, 4 successes. How many ways can that happen? Well, there's only one way. Right, coming back over here. This is it. That's the only way that can happen. So, put them over here. There's just a 1. 1 times all that, right? Because there's only one way that we can have 4 successes. The case of success, 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 success. Good. So the pattern is actually pretty easy, right? At least this part of it is easy. We're going to multiply the number of successes times the number of failures, and we got to raise it to the corresponding powers, right? So this has to match with that because we're keeping track of successes. 0 successes, so the probability of success to the power of 0 times probability of failure to the power of the number of failures we have. Knowing that they're binomial situations, either you had a success or a failure. So if you had 0 successes, then you must have 4 failures. Okay, so here is our table. We can use our calculator now and convert this into decimal values. So if you notice this on your calculator, this e with -5, this is scientific notation. This means that this is times 10 to the power of -5, which means that if you want to rewrite it this way in expanded form, you would have to move this decimal place to the left by 5 spaces, which means that there would be 4 zeros in front of the between the decimal and the 2. Okay, that's what this means. So I'll write it down this way. 2401 right? And then this represents 0.12342401. That's what that means. You move the decimal space 1, 2, 3, 4, 5 different spaces to the left. So it's a really small number, right? It's just a way of expressing a very small number. We'll start running into that a lot moving forward, cases like that. And then often those are rounded to 0. You'll see that our textbook, when we look at tables and stuff, very often just rounds that to 0. Okay, so there's our pattern. I think this part over here, this part of the pattern, the multiplication of the probability of success, probability of failure to the power of how many successes and how many failures, that part is pretty straightforward, I think. The pattern is easy to do. So, when I'm creating these, really I just copy down 0.07 times 0.3, 1, 2, 3, 4, 5 times. And then I come back over here and just simply point out the powers. And you can do this nice pattern where they kind of count. So this matches with this, and then this matches with this, and then this matches with that, and then this matches with that, and then this matches with that. And then for the failures, they have to add up to 4. So this is 4, then that adds to that. So there's this nice countdown of 0, 1, 2, 3, 4, and then the other way around, 0, 1, 2, 3, 4. So this part of it, I think, is really easy. It's these numbers that are a little more difficult to find. The 1 and the 1 from the outskirts, okay, those aren't so hard to figure out because there's only one way to get 0 successes and there's only one way to get 0 failures. But these other ones of how many ways are there to get exactly 1 success, how many ways are there to get exactly 2 successes, this 4, this 6, and this other 4, these are a little bit more difficult to get. But if you go back to chapter 5, and we think about how many ways are there to get 2 successes when we have 4, right? So like to figure out this 6 right here, for example, when x equals to 2, how many ways are there to get 2 successes when we have 4, right? We have 4 different trials. Let's forget the f for a second. Let's just think about how many ways are there for me to put 2 s's anywhere. So I can put an S here and an S there. That's one way to do it. Or I can put an S there and an S there. That's another way to do it. Or I can put both S's there, right? So there's all kinds of ways in which I can put 2 S's down in these 4 spots. Okay, so let's rethink this a little bit. Let's think about having a number for each spot. So this is spot number 1, spot number 2, spot number 3, and spot number 4. So this is the scenario of having a 3 and a 4 out of 4 chosen. Whereas, on the other hand, let me zoom out a little bit. Whereas, on the other hand, what if I had the scenario of 1, 2, 3, 4? What about the case where I put an S here and an S there? This is the scenario of 2 and 3, right? This is 1, 2, 3, 4. So this is a scenario of spot 2 and spot 3 have an S, right? So what I want to do is think about all the ways in which I can choose 2 out of the 4 numbers. You cannot pick the same number more than once. So we don't want to consider the cases of like 3, 3, where we chose 3 twice, because that would mean both S's are in the same spot. That doesn't make sense. So we're not going to allow the same letter to be chosen more than, the same value to be chosen more than once. So that's without repetition. And the order doesn't matter, because the case of 2, 3, we want this to count the same as the case of 3, 2. Either way, there's an S in the 3 spot, there's an S in the 2 spot. I want them both to count as the same. So order doesn't matter, repetition doesn't matter. I want all the number of ways in which we can pick 2 numbers out of 4. So we want to count the number of ways to select 2 out of 4 values where the order doesn't matter, where order does not matter, and there is no repetition, right? You can't pick the same number more than once, and no repetition. So if you remember from chapter 5, this is exactly combinations. This is combinations of 4 choose 2 items. Good. So this will tell you this number. Combinations of 4 choose 2 is equal to 6. Let's double check that on our calculator. And we have a nice easy button for that on our calculator too, if you recall from chapter 5. So let's go to 4 math combinations right there. 4 choose 2, enter, and we get a 6. 4 choose 2 is 6. And for the other one, for example, let's say this one, how many ways are there to get 3? 3 out of the 4. So that would be combinations of 4 choose 3. 4 math probability down to combinations, choose 3. And you see that there are 4 ways to do that. That's how we can get this 4. Okay, so we have everything we need to come up with a really nice, easy formula for figuring out the probability distribution table for a binomial random variable. Okay, let's look at the formal presentation of that formula. Okay, finally, the binomial probability distribution function. Everything we've done up to now is just so that we can get to this formula and understand where it comes from. Like I said earlier, I hope that didn't scare you off with all the work I've been doing so far. You are not required to do all of that. Hopefully you were able to kind of follow and you were able to see the patterns that were emerging so that we can understand where this formula comes from. But this formula is what we're going to use to solve the problems in your homework for some of them. And for some of them, we're going to use some tables and calculators and other things, but you won't be asked to expand it all out the way I've been doing it. So binomial probability distribution functions, the probability of obtaining x successes in n independent trials of a binomial experiment is given by this formula. There's sort of 3 pieces to it. I know it's all mixed up, but there's really like 3 kind of pieces to it here. One is the probability of getting x successes is equal to the probability of success to the power of x. Remember, we're kind of counting how many s's are there, how many successes are there. So this matches with that exponent. And then we multiply it times the probability of failure. Remember, 1 minus p is the probability of failure. And then we raise it to the power of the number of failures, remembering that everything is either a success or a failure. So it must be the case that this exponent plus this exponent add up to n, right? And so that's how we get to this. If we have n independent trials and we're looking at x successes, then there must be n minus x failures, right? The rest of them are failures. If x, for instance, is equal to 2, just to kind of make sure we're kind of understanding this, if in a, for example, if n equals to 2, and let's say capital N equals to 10, we're looking at a case where there are 10 independent trials, and we want to know the probability that x equals to 2. So we find the probability of success and raise it to the power of 2. There are 2 successes, probability of success, the power of 2. And then the probability of failure is raised to the power of the rest of them. If n was 10, 10 minus 2, this whole thing will be equal to 8, right? 10 minus 2, 8. These two must add up to the n value. Good. And the only thing that the third part is this one, the combinations, because we have to know how many different ways are there to do that. Remember that here in this situation, x equals to 2, we don't care about order here, but we have to think about all the specific ways that can happen so that we can account for this value. And so this is combinations of, and in my little situation, this one was 10, and this would be 2. So combinations of 10 choose 2 will tell you how many ways there are for this to happen when order is taken into consideration. Okay, so this is the formula we're going to use. Let's apply it in a specific situation. Okay, so for example, according to the CTIA, 72% of adult Americans would rather give up chocolate than their cell phone. In a random sample of 10 adult Americans, what is the probability that exactly 8 would rather give up chocolate? Okay, so is this a binomial? First of all, you have to think about that. Does it satisfy all 4 conditions? Is there a fixed probability? Yes, 72%. Is there a fixed number of trials? Yes, there are 10 trials. In this case, n equals to 10. Are the trials independent? So when you pick one randomly selected American, whether they said yes or no, is independent of whether another randomly selected American says yes or no. And there are 2 mutually exclusive outcomes, right? This is just a simple yes or no question. So yes, it satisfies the conditions, and so we can use our formula to solve this. Instead of doing the whole crazy long table to figure out all the possible outcomes and then count them and see how many of them would be the cases where we have 8 out of 10, we can just jump right to our formula, right? So using the formula, we see that x equals to 8 is going to be equal to combinations of 10 choose 8 times the probability of success. Well, let's put that over here. N equals to 10. Probability P of success, probability of success is 0.72. And then 1 minus P, which is often referred to as Q, is also referred to as Q, is equal to its complement, which is going to be equal to 0.28. If there's a 72% chance that they will say, yes, I'd rather give up chocolate than their cell phone, then the complement of that, someone saying, no, I wouldn't do that, that would be a 28. Okay, so then the formula says to multiply the probability of success, which is 0.72, to the power of the number of successes we are counting, which is 8, times 0.28 to the power of, and it's n minus x, so in this case it's 10 minus 8, which we know is equal to 2, right? Because they have to add up to this 8, right? So I'm just going to erase the 10 minus 2 and just write it as a 2. Just looks neater as a 2, right? And then this combinations here is what tells us the number of ways that can happen. And if we know from chapter 5 that this is equivalent to having, what's the formula for this? It's 10 factorial divided by 8 factorial times 10 minus 2 factorial. Right, that's that formula, 0.72 to the power of 8, 0.28 to the power of 2. Right, so all we have to do is figure this out, and we'll get our answer. And we can either crunch this out, or we have a nice easy button on our calculator to figure out that guy. So let's figure it out. So, clear, there are 10 math combinations of choose 8. So that's going to tell us the number of ways this can happen, and we want to multiply that times 0.72 to the power of 8 times its complement, which is 0.28 to the power of 2. Right, so that's this right here. We can hit enter, and there's our answer. 2548. 0.2548. Okay, what does this mean? There's a 25% chance that this is the outcome. Okay, so let's say that, okay, so the sample has size 10. So let's say that we repeat this 1,000 times. If 1,000 samples each of size 10 are taken, right? So you can kind of picture that. It's a lot of people, right? So we have a little group here, 10 people. That's just one sample. And then the second sample, another little group of 10 people. And then the third one, and then the fourth one, right? So we do this 1,000 different times, 1,000 different groups, each of size 10 people. So when we do this, we will find specific answers to these, right? Maybe this first sample, it turns out that exactly 2 people said yes. In another sample, maybe it turns out that maybe 8 people said yes to that one, and so on and so forth. So we expect that about 25.48% of these samples will result in seeing x equals to 8, right? 25% out of 1,000, that's about 254, it rounds up to 55. So we'd say about, we expect about 25.48% of the 1,000 samples, or about 255 of the 1,000, to result in x equals to 8. In other words, x equals to 8, meaning that in that group, exactly 8 people said, yes, I'd rather give up chocolate than the cell phone. Right? That's the interpretation for it. Okay, part B, fewer than 3 would rather give up chocolate. Okay, so we have to be careful about the language. Fewer than 3. Fewer than means less than, strictly less than the number that they give you. So probability, this is the probability that x is fewer than 3, means that it's strictly less than 3, which means that we're looking at the cases when x equals to 0, or x equals to 1, or x equals to 2. These are all the cases where the value is less than 3, fewer than 3. Okay, and so we know that because we have addition symbols here, or statements, we have addition symbols. So this is equivalent to the probability that x equals to 0, plus the probability that x equals to 1, plus the probability that x equals to 2. Good? And so now we can apply our formula for each one of these. And so for the first one, we know that this is going to be combinations of 10 choose 0. And it's going to be the probability of success, 0.72 to the power of 0 successes, and 0.28 to the power of 10 successes. 10 successes, 0 successes, 10 fails. That's this case. Plus, now combinations of 10 choose 1. And this is the case where we have exactly 1 success and 0.28 to the power of 9 fails. Plus, combinations of 10 choose 2. And this is the case where we have 0.72 to the power of 2 successes, and 0.28 to the power of 8 fails, right? So notice the patterns. These two numbers always add up to 10 because we have a total of 10 trials. Add up to 10, they add up to 10. Good. Okay, so now we can use our calculator to figure out each one of these probabilities. Okay, remember that this is scientific notation, so that means that it's just a really small value. We got to move the decimal over 6 spaces to the left, which means we'd have an extra 5 zeros here. 2962. Right, so I move the decimal space 1, 2, 3, 4, 5, 6. So there's 5 zeros, then 2962. Okay, that's this one. And also note that I was just kind of writing out into our calculator, but really this represents a 1. The number of ways to get 0 out of 10, there's only one way. So this really just becomes 1. And any number raised to the power of 0 is just 1. So this is really just 1 and a 1. So I could have gotten the same answer by just punching this into our calculator. So note that 0.28 to the power of 10 would give me the same answer. Right? This is really 1, this is really 1. But I just put it in there so you can see the pattern. Okay, so then the next one, over here maybe, 10 combinations of 1. Okay, combinations of 10 choose 1 times 0.72 to the power of 1 times 0.28 to the power of 9. Let's multiply that out, and we get that. So a little bit smaller. It's still a scientific notation, still represents a very small value. And we move the decimal over 5 spaces, which means we'll have 4 extra zeros there. And 76. Okay. So 7616, and we move the decimal over 5 spaces. So there should be 4 zeros. 1, 2, 3, 4, and then that space, the extra space. So in total, we moved it over 5 spaces. From here, 1, 2, 3, 4, 5. Okay, finally, the last one. We have 10. Okay, so this last one is going to have scientific notation to the power 10 to the power of -4. So move the decimal space 4 spaces. So now there's going to be 3 zeros. So 8813. So there we are. These 3 numbers we add together, and that'll give us this probability. So now we add these 3 values together. Add that up, and we end up with this 9604. 0.1239604. A pretty small number. Okay, so probability that there are fewer than 3, which means it could be 0, a 1, or a 2, right? Any one of these 3 cases satisfies this statement, is equivalent to finding out the probability of each one separately using our formula and then adding them together. And so that's what this is. Probability that x is strictly less than 3. Right? And this is, I'm just being lazy, it's the same. You can just copy it all. Okay, so now for the interpretation. Because our probability is so small, I'm going to step it up a little bit and say 10,000 tries. So let's say if 10,000 groups of trials of each size 10. Groups or trials, each of size 10 are taken. Right, so we have that. We can visualize that. Group number 1, there's 10 people there. And then number 2, 10 people there. Right, and so on and so forth. And we do this for 10,000 of them. Way down here, there's 10,000 of these groups. So there's a lot of these groups, 10 people. Okay, so each one of these groups, we're going to ask them the survey question. Would you rather give up chocolate than your cell phone? And then for each one of them, we're going to have some value of x. How many people in this group said, yes, I'd rather give up chocolate than my cell phone, was the question. So then x equals to maybe 4 happened here. And maybe here x equals to 7 happened there. Right, and the one after that, maybe that one's x equals to 1 right after that, and so on and so forth. And then if we come back and count how many of those results satisfy this statement, that x was either 0 or 1 or 2, right? Like this is one of them. How many of them? Well, this is the percentage of the 10,000 that we would expect would satisfy that, right? So if 10,000 groups, each of size 10 are taken, we would expect about, and then we multiply those two values, 0.000996, 9604 times the 10,000, and that gives you about 9.6. So we would expect about 9 or 10 of the groups, of the 10,000 groups, to have an x value of 0 or 1 or 2, right? That in that group, nobody said yes, or maybe exactly one person said yes, or maybe 2 people said yes, right? So not very many. Out of 10,000 different groups, we expect only about 9 or 10 of those groups to have 0, 1, or 2, right? A pretty rare occurrence. Part C, at least 3 would rather give up chocolate. What's the probability that at least 3 would rather give up chocolate? So this is the probability that x is greater than or equal to 3, right? At least 3 means 3 or bigger. So keeping in mind that there was 10 people being surveyed, that means that probability that x equals to 3, or x equals to 4, or x equals to 5, or x equals to 6, or x equals to 7, or x equals to 8, or x equals to 9. Oh, this looks painful. Or x equals to 10. Or x equals to 10. Okay, so then that means that we have to figure out all of these probabilities separately. Probability that x equals to 3 plus probability that x equals to 4 plus dot, 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 all the way out to the end here, plus the probability that x equals to 10. That sounds incredibly painful. And each one isn't too bad, but there's so many of them, and it's so much work to figure out each one of them, that instead we're going to do the following. We're going to realize that, if we look at the distribution table for this thing, for the random variable, we know it looks like this. Here's a random variable. X can take on 0, or x can take on 1, x can take on 2, x can take on 3, x can take on 4, x can take on 5, x can take on 6, x can take on 7, x can take on 8, x can take on 9, x can take on 10. Right? These are all the values, and then to the right, we would figure out the probabilities of each one of these. Okay, I don't have them, but it doesn't matter. We know that for this to be a proper probability distribution, the sum of all of these on the right has to add up to exactly 1, right? They have to add up to 100%. So if we add these up, add these probabilities up, these probabilities here have to add up to 1. So they are asking us to figure out the sum of all of these. In fact, let me get a... they're asking us to figure out these, the probability of the sum of all of these guys here, right? That's a lot of work to figure out all of these guys. But they have to add up to 1. All of them have to add up, and we already figured out this one. This one was the probability that x was less than 3, right? We already figured out the sum of these three values in the previous example, so we can take advantage of that. So we're going to come back over here and do the following. We're going to say that the probability that x is greater than or equal to 3 is equivalent to the complement of 1 minus the probability that x is strictly less than 3. Right? So the probability that x equals x, the probability that x equals, so the probability, another way of looking at this, the probability that x equals a 3 or a 4 or a 5, all the way out to 10, is equal to 1 minus the probability that x equals 0 or 1 or 2. Right? Again, taking advantage of the fact that they all have to add up to 1. Good. So I don't have to add up all these individually when I already know the answer to this one. This one we already saw from the previous example. In fact, we still have it here. That equals to this. The sum of these three was 3 zeros and 9604. 9604. Right? That's what this answer was. The sum of these three values, x equals to 0, x equals to 1, x equals to 2, equal this value. So therefore, the rest, all the way up to 1, has to be the sum of these values. Good? Okay, so back to this guy. Probability that x is greater than or equal to 3 equals to 1 minus the probability that x is strictly less than 3, which means that this is 1 minus 0.123964. Or, okay, let's put them on our calculator. This is going to be 1 minus 0.123964, which gives us 99904. 12304, right? Which is a very high likelihood. Probability that x is greater than or equal to 3. It's 99.904%. Good. But so we just highlighted how we can take advantage of the table and knowing that the summation of all the probabilities has to add up to 1 to be able to find the complement. So that'll shorten our work from time to time. Okay, now let's take a look at this example. First, we're going to use the formula once again, and then we're going to learn how to use technology, how to use our calculator to solve it. Okay, so according to the Gallup organization, 65% of adult Americans are in favor of the death penalty for individuals convicted of murder. In a random sample of 15 adult Americans, what is the probability that A, exactly 10 favor the death penalty, and B, more than 6 favor the death penalty? So first of all, we got to ask ourselves, does this satisfy the conditions for a binomial random variable? Right, there are 4 of them. Number 1, and in no particular order, the probability of success is fixed. It is, right? It's 65% of all Americans out of 320 some odd million Americans. 65% of them favor the death penalty for individuals convicted of murder. So if we randomly select 15 Americans, we can assume that that probability of success is going to be approximately constant, about 65%. The outcomes are binomial, right? So first, let's confirm that this situation satisfies the conditions of a binomial random variable. Okay, so remember there are 4 of them in no particular order. Number 1, there are a fixed number of trials. And that is true here, right? There are 15 Americans that are going to be randomly selected, right? So for us, that means that I'll start putting the solution to part A here. A. So N is equal to 15. We have 15 adult Americans that are going to be surveyed. Number two, the trials are independent. They're randomly selected Americans. So if the third person is randomly selected and asked, do you favor the death penalty for individuals convicted of murder? Their response will not depend on what the prior people have said, right? They have their own opinion, their own independent opinion. So they are approximately independent. For each trial, there are two mutually exclusive outcomes. And that's true because you phrase it in a way that there's only going to be two possible outcomes. Yes, you support the death penalty for individuals convicted of murder, or no, you don't support the death penalty for individuals convicted of murder. Right? So you phrase the question in a way so there's only two possible outcomes, so it satisfies that condition. And the probability of success is approximately constant. Because the 65% refers to all Americans, 320 odd million Americans, 15 individuals selected from that population will mean that 65% will be approximately the same from person to person to person. Okay, so it satisfies all the conditions. Let's answer part A using our formula. That should be pretty easy. So the random variable is 15. That means that there are 16 possible answers when you include 0, right? Okay, so now for part A, we want to know the probability that exactly 10 favor the death penalty. So that means that we're looking for this, the probability that x equals to 10. And we know from our formula that means it's combinations of 15 choose 10. This will tell you all the different ways in which we can choose 10 out of 15 who favor the death penalty, right? Remember, this doesn't care about order. They just want to know 10 out of the 15. It doesn't matter what the order was in which you selected them. But in order to find that probability, we have to think about all the different ways in which you can reach this result of 10 out of 15 when order does matter. Okay, so then next we multiply times the probability of success. Probability of success P in this question is just going to be equal to 0.65%. Good. So then we're going to multiply this by 0.65% to the power of 10 because we're looking for 10 successes. And well, if the probability of success is 65, that means that the probability of failure, Q, is equal to probability of fail. So that means that you find someone that doesn't support it, right? Remember again, success is not necessarily a good thing. It's just the thing we're counting, the thing we're looking for. And we're looking for individuals. We're counting how many individuals favor the death penalty. So the failure rate here is going to be its complement. They have to add up to 35. They have to add up to 1, so that means that this has to be 0.35. Okay, so we're looking for 10 successes out of 15 being surveyed, which means there must be 35 failures. There must be 5 failures. So it's 0.35 to the power of 5. Good. So 10 successes, right? There's a probability of success. And then 5 failures, right? And we multiply these two things together. And then this number tells us how many ways there are to find 10 successes amongst 15 trials. Good. Okay, so now that we have our formula, we can use our calculator to find this result. And let's figure out what this is first. Let's come over here. So 15 math combinations and 10. 3,003, right? That's a pretty big number. There's a lot of ways to do this. So this is going to be 3,003 ways in which this can be accomplished. We'll look at a couple of possibilities here. 65 to the power of 10, 0.35 to the power of 5, and all of this is the probability that x equals to 10. Right, so this 3,303, remember we have 15 people, so that's 1, 2, 14, and 15. Okay, so we have 15 individuals, right? You can kind of think of, I don't know, chairs or something. You put 15 chairs out, and we're going to sit down people, and we want to know how many ways are there to select 10 out of 15 that are in favor. So we just have to think about all the possible ways in which we can lay down 10 S's into this, right? Maybe this one's a success, this one's a success, this one and this one's a success, this one's a success, maybe this one's a success, success, success. That's 1, 2, 3, 4, 5, 6, 7, 8, 9, 10. Here's one way that that can be accomplished, right? Another way would be if maybe instead of this one, instead of that one, maybe it was this one that was a success. That's another way to do it. Or maybe instead of that one, maybe it was this one that was a success. So there's a lot of ways in which 10 out of 15 people can be chosen when order matters. And that's what this 3,303 is all about. There are 3,003 different ways in which all of this can occur. And each one of those is going to have this probability. Okay, all right, so we don't really need that. I just wanted to, once again, kind of go over what this number means. But we don't really need it. Let's get rid of it. Let's get back to this guy. Okay, so now let's get an actual numerical answer for this. Probability that x equals to 10 is equal to, and let's go to our calculator. So it's going to be 3003 times, and then it's going to be 0.65 to the power of 10, close parentheses, times, and then it's going to be 0.35 to the power of 5. Enter, and there it is. Our answer is 2123. 0.2123. Okay, so here's our answer. Let's think about what that means. So what this means is that if we have a large group of trials where each trial is exactly a group of 15, right? So the large group of trials could be any random number, but usually we like to use a nice big round number to explain it. So usually either 100 or 1,000 seems like good choices. So let's say 100. So if 100 groups of 15 people each are randomly selected, we expect about 21, right? It's 21.23, but about 21 to 22. So about 21 groups out of the 100 of the 100 to have exactly 10 out of 15 people in that group, to have exactly 10 people favor the death penalty. To have exactly 10 people favor the death penalty. Okay, so if 100 groups of 15 people each, right, so we kind of visualize that. Group number 1, here's like 15 people here. 15 people. Group number 2, okay, another randomly selected 15 people, right, and so on and so forth. And we do that for 100 different times. Right, so there's this last group, also has 15 people. And then we go through and we ask individuals in each group, do you favor the death penalty for individuals convicted of murder, yes or no? And each group is going to have their own response rate here. So maybe for this case, maybe 8 people said, yes, I do favor the death penalty. Maybe x equals to 8. for that first one. Right? I'm just making up a random number here. For the second group, maybe in this group, maybe this is one of the ones where where 10 people said yes, right? Maybe the group after that, maybe only 3 people said yes. Maybe, you keep going, keep going. Maybe the very last group over here, maybe in this last group, 11 people said yes, yes, we do. Okay, so there's going to be 100 different results, and chance is going to play a role. So it's not always going to be exactly what we expect, but over the long run, we know by the laws of statistics that we have a good chance. The most likely outcome is going to be that 21 out of those 100 will have 10 say yes, exactly 10. Okay, so hopefully that makes sense. All right, well, let's see how technology could have helped us solve this even faster. So we have our formula, and the formula makes things nice, way better than having to, figure out all those probabilities the way we did it in the first couple of examples. But even better than the formula, we have some nice easy buttons in our calculator. So let's see how we could do that using our calculator. Okay, so I'll put a big OR here. Big OR. Using our technology, we're going to use calculator functions to solve the exact same thing. So we're going to put probability that x is equal to 10. That's what we're looking for. And this is going to be equal to a calculator function called binom PDF. Make sure you choose PDF. I'll show you where to get it in your calculator in a second. So it's binom PDF. And the calculator is going to want 3 numbers. It's going to want you to put the value of n, the number of trials here, comma, then the value of p here, the probability of success, comma, and then the value of x here. Right, let me point those out. So this is going to be your n value goes there, your p value goes there, and then your x value goes there. So in this particular example, for us, we had 15 trials. 15 people are going to be randomly selected and asked if they support the death penalty for individuals convicted of murder. The probability of success is 0.65 for this example. And we're interested in figuring out the probability that exactly 10 out of those 15 support the death penalty. So for us, the x value is going to be 10. Okay, so this is what we're going to type into our calculator. Let me show you where to find it. So we go over to our TI 84 or 83, and we're going to go over to where it says distributions. This little button right here, it's above the button that says bars. So we first of all have to hit the second button. The up arrow will be highlighted. It will start blinking. And then you can hit this, and so now you get the distributions, and this is what the menu looks like. We're eventually going to learn all of these. So this is starting in Chapter 7, we'll start using some of those functions. But for now, we need to use our arrow to come down, 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 down until we run into binom PDF. Now be careful because there's also a binom CDF. That one we'll look into next. But for now, we definitely want binom PDF. Okay, so now depending on the model of your calculator, these values might be a little bit, this menu might be a little bit different. So let me show you this. The more recent menus will have this. They kind of walk you through it. Number of trials, right? It was 15. The probability of success, 0.65. And the x value is 10. Good. So we type those values in, and then hit paste, and it takes you to the main screen again, where it's written it out like this. Some of the older models might not have that little in-between menu that helps you fill in these values. Some of the older calculators, when you type in binom PDF, it automatically brings you to this screen, and then this is blank, and this thing is blinking right there because it wants you to type it in. So if you have one of those calculators, you have to type in 15, and then you have to use this button that has a comma, and then type in 0.65, comma, and then 10, and then close parentheses so that you achieve this, right? So people had a lot of trouble with that in the older models. it brought you to this screen and these things were blank, and then people didn't know how to complete the statement. So the newer models introduce that intermediate screen that helps you fill it out by asking you what are the trials, what's the probability of success, and what is the value of x. So that's what you get here. Either way, so you get to this point, you type it all in, and then you hit enter, and you see that we get the exact same answer. Binom PDF 15, 0.65, 10 is the same thing as the value we get from our formula over here, right? 0.2123. Much easier, right? Faster and easier. So this gives you the same result, 0.2123, right? Same. Okay, so for me, there will be questions on the test where I specifically say use the formula, right? So then I expect to see something like this up here, right? Use the formula, I expect to see something like this up here. And I want to see what values you plugged in, just set up the formula, and then use your calculator to punch it all out and get an answer, right? But there will be many questions where I also say, you don't have to use the formula, you can use your calculator. So use the functions in your calculator. That's the binom PDF, and in a minute we'll see how the binom CDF is also useful to solve it. So then I expect to see this. So even if you get to use your calculator to find the answer, on your written in-class exam, this is what I'm expecting to see, right? This is how I know what values you typed into your calculator so that I know how you got your answer. If you only give me this as an answer, you're not going to get full credit, right? Writing this with the appropriate values is part of the solution, even if you get to use your calculator. Okay, so if I say use your calculator to solve this, then I expect to see something like this. If I don't give you instructions on whether to use the formula or not, then it's up to you. But if it's up to you, I think you'd probably want to use this method, right? Much easier, much faster. Okay, hopefully that's clear. And then the interpretation is exactly the same, right? We get the same result, same interpretation. Let's look at part B now. Okay, so we answered part A, exactly 10 favor the death penalty. Part B, let's find the probability that no more than 6 favor the death penalty. So no more than, that language, we have to get used to some of these ideas. Less than, more than, no more than, no less than. So let's look at some of those interpretations. Okay, so okay, so these are some of the phrases we got to get comfortable with. So for example, if you're reading a word problem and it says at least, no less than, or greater than or equal to, it means that we are looking for a value that is equal to that value or greater. So for example, if we say x is at least 5, this means that x is greater than or equal to 5. Right? We include the 5 or bigger. Good. Up until, for binomial, up until the value of n, right? N is the most that x could possibly be. Same thing for no less than. X is no less than 7. Well, this means that x is greater than or equal to 7. Good. Same thing with greater than or equal to. More than or greater than means that it has to be larger than that value, but we do not include it. So if we say y is more than 3, that means y is strictly greater than 3. Good? Okay. Fewer than or less than, again, we have to go below that value, and we do not include that particular value. So if we say w is fewer than 9, then w is strictly less than 9. Good. And then finally, more than or at most or less than or equal to. So no more than, at most, or less than or equal to. That means that we got to go below that value, but we also get to include it, right? So if we say Q, well, let's not use Q because that might get confusing. How about B? B is no more than 8. That means we got to go to 8 and below, but we include the 8. So this translates into B is less than or equal to 8. Okay, so these are some of the phrases that we use. Exactly is usually not a problem. Exactly, equals, or is all translate into an equal statement. Okay, back to our problem. Okay, so we are asking 15 individuals whether or not they support the death penalty. And we already answered part A. Part B says find the probability that no more than 6 favor the death penalty. So this is just for part B. Let's find the probability that no more than 6 favor. Let's just put favor. So we now know that no more than 6 means that we include the 6 and go below. Right, so this is equivalent to finding the probability that x is less than or equal to 6. That means that the cases that will satisfy it is if in a group of 15, 0 of them favor it. That's part of this. Or maybe in a group of 15, 1 of them favors it. That's part of this. Right, all the way up to 6. So this is equivalent to saying find the probability that x equals to 0, or x equals to 1, or x equals to 2, or x equals to 3, or x equals to 4, or x equals to 5, or x equals to 6, right? All 7 of these, right? When you include the 0, we got to go one more. So there's 7 possible options here. These make up this statement. Okay, so we know that they're all or statements. That means we have to add them all. So we have to find them all individually and then add them. Probability that x equals to 0 plus the probability that x equals to 1 plus the probability that x equals to 2 plus the probability that x equals to 3 plus the probability that x equals to 4 plus the probability that x equals to 5 plus the probability that x equals to 6. 7 of them. Okay, well, if we had to use our formula for each of these, that would be painful, right? Let's just start setting it up, but we're definitely not going to do it that way. So the formula would tell us that this is combinations of 15, choose 0, 0.65, probability of success to the power of 0, times 0.35 to the power of 15, right? If there are 0 successes, that means that there were 15 failures. And that takes care of this guy. Plus, now this one, combinations of 15, choose 1, 0.65 to the power of 1. Now we have 1 success out of the 15, times 0.35 to the power of 14. 14 failures, 1 success. That takes care of this one. 2 down, 5 to go. Probability of combinations, choose 2, 0.65 to the power of 2, 0.35 to the power of 13, right? So if there were 2 successes, there must be 13 failures. Okay, let's just jump over to the end, dot, dot, dot. We see the pattern. And then the very last one over there, this one would be combinations of 15, choose 6, 0.65 to the power of 6, 6 successes, which means there must be 9 failures, 0.35 to the power of 9. Okay, so this is how we would get our answer using the formula. Lots of work. So we can use the shortcut we just learned about our calculator functions, binom PDF, to simplify this process a little bit. So let's scroll down a little bit. Right, so this is the same thing as saying, instead of typing all this into my calculator, I can just put binom PDF of, and it's going to be 15 comma 0.65 comma 0, and that takes care of that one, plus binom PDF of 15 comma 0.65 comma 1, that takes care of this one, plus binom PDF of 15 comma 0.65 comma 2, that takes care of that one. And again, we see the pattern, dot, 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 plus the last one. So the last one being binom PDF of 15 comma 0.65 comma 6, right? And this will give us this one right here, probability that x equals to exactly 6. So we have 7 different values that we need to find on our calculator, and then we need to add them all together. So we could do that, but there's an even better way of doing this. The calculator has a separate function called binom CDF. Binom CDF is exactly what we need to do here. It's the cumulative values starting from 0 all the way up to where you tell it to stop. So instead of doing all this work, we can just do one single function, binom CDF of 15 comma 0.65 comma 6, and by the fact that we chose CDF instead of the PDF in our calculator, the CDF is the running sum of the values of the PDF starting at 0 and going up to where you tell it to stop, which is exactly what we need for this solution, right? We need to be able to add up this result plus this result plus this one, right, all the way up to 6, and that's what we'll get from here. So makes life even easier. Let's see how that works out. So let's go to our calculator, and let's type this guy in here. So we're going to go to math. I'm sorry, we're going to go second, distribution, and then we're going to go down, 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 and make sure to choose binom CDF. Binom CDF, enter. And then there are 15 trials. Probability of success is 0.65. And the value of x is equal to 6. And we want to paste that. There it is. Hit enter, and there's our answer. 0.0422. 0422. 0422, which is a little over 4%, right? So it's a pretty small likelihood that in a group of 15, we will get either 0, or we will get 1, or we will get 2, all the way up to 6 results, right? So it's still a fairly low likelihood of receiving such a result. Okay, so interpretation, what that number means. So again, let's say that we had 100 trials, each of size 15. So here's trial number 1. We take this group, and there's 15 people in this group. 15 people, right? This is because n is equal to 15. Number 2, there's another group. Here's a separate, completely unique group of people, randomly selected, group of 15. Then there's another one, 15 people. And we keep going, dot, 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 dot. You know, the 100 is kind of arbitrary. Let's just pick a different number. Let's say 1,000. So let's go all the way down, and there's 1,000 groups. 1,000 groups, each of size 15 people. 15 people. Okay, so we have all these groups, and then within each individual group, we'll have a certain value of people, a certain number of people that are in favor of the death penalty. So I'm just making these numbers up. Let's say group number 1, maybe it just so happens that x equals to 9. 9 people in that group said, yes, I favor the death penalty. We go to the next one. Maybe the next one, only 2 people said, yes, I favor the death penalty. The third one, maybe here, maybe all 15 favor the death penalty. Good. Maybe the one after that, the group after that, maybe only 5 favor the death penalty, right? So it varies. It's random. And if we keep going all the way throughout, the very last group will also have a value. Maybe in the very last group, 6 favor the death penalty. Okay, so now we do this for 1,000 groups, and then we come back and count in how many of those groups do we see either 0 people favor, 2 people favor, 3, 4, 5, or 6, right? So in just the numbers I invented here, we would see that there were 3 groups that did it. Okay, well, what this tells us, if we multiply the 0.0422 times 1,000 groups, that turns into about a 42.2, right? Move the decimal space over 3 times. So about 42 groups are expected to have those values, right? So if 1,000 groups in each of those 42 groups, we expect about 42 groups to have either 0 or 1 or 2 or 3 or 4 or 5 or 6 people in each of those groups. Okay, so hopefully things made sense. So we have the binomial probability distribution function that will give us each of these individual values. In this particular question, we needed to find 6 of them in order to answer this question. So that would mean applying that formula 6 different times. Not difficult, but pretty tedious, right? So then we learned about this Binomipedia function in our calculator. That's the second tool that we have to answer these questions. And the Binomipedia formula is exactly this one. It gives you the exact value as that. It's just a shortcut that we get to use with our calculator. So we can do that. But then again, it still requires us to type in 6 different things into our calculator and then add them together. And then finally, we introduce this Binomipedia function in our calculator, which gives us the running sum of the values of the PDF function from 0, always starting from 0, all the way up to and including the value you tell it to stop at. Good. And the interpretation hopefully made sense. All right, let's move on to finding the means. Okay, objective number 3, compute the mean and standard deviation of a binomial random variable. If you recall from section 6.1, the formula for finding the mean of a random variable and the formula for finding the standard deviation of a random variable is pretty ugly. It's pretty intense formula. That formula still works for binomial random variables. You can get the correct answer by using that formula. But one of the advantages of recognizing that it's a binomial random variable is that there's an easier, faster way of finding the mean and standard deviation. The formulas are a little bit more simple, right? So these only apply to binomial random variables. The other formulas from 6.1, they are sort of the overarching formula that applies to any discrete random variable. So you'll get the same answer, but if you can avoid doing work, why not, right? This is an easier, better way of doing it. So a binomial experiment with n independent trials and probability of success p has a mean and standard deviation given by these formulas. The mean of our random variable x is equal to n times p, right? The number of trials times the probability of success. Very easy formula. Just got to multiply 2 numbers instead of doing that other formula from 6.1. And the standard deviation is also very easy. It's the square root of n times p times 1 minus p. Now remember, 1 minus p is the probability of failure, right? P is equal to probability of success. 1 minus p is the probability of failure. So the way I like to remember this is to say that the standard deviation is equal to the square root of NPQ. Just easier, faster, shorter, but it means the same thing, right? P is the probability of success, Q is the probability of failure. So this is where probability of success equals to P. Probability that you fail or failure is equal to 1 minus P, which is also equal to Q, right? We also use that letter there. So it just makes it a little easier to remember. But again, a very, very easy formula to apply, right? So if you apply the formulas we learned in 6.1, you'll still get the same answer, but it's a lot more work, right? That's one of the great benefits of recognizing that we're working with a binomial random variable. The mean and standard deviations are very easy to calculate. Okay, let's look at an example. Okay, so according to the CTIA, 72% of adult Americans would rather give up chocolate than their cell phones. In a random sample of 300 households, determine the mean and standard deviation number who would rather give up chocolate than their cell phones. Okay, so we ran into this question earlier, so we know that it does satisfy the conditions of a binomial random variable. And here we know that n is equal to 300. 300 individual households are sampled. And we know that probability of success, which is just equal to P, P equals to 0.72. And the probability of failure, which we know is 1 minus P, which I also like to use the letter Q, all of this is equal to its complement of this, right? Either a success or a failure. So that means that this is 0.28. These two things must add up to 1. Okay, so that's all we really need um, for to determine the mean and standard deviation. So the formula for the mean, mu of the random variable x, is equal to n times p. Really simple. So the mean of the random variable x is equal to 300 times the probability of success, which is 0.72. Good. So random variable is equal to 300 times 0.72. Good. So about 216. 216. And the standard deviation, sigma, of the random variable x is equal to, and again, I like to memorize it as NPQ, NPQ, square root of NPQ, right? Again, that's the same thing as NP1 minus P. However you like to memorize it is fine. I just find it easier to go NPQ. So this is going to be the square root of 300 times 0.72 times 0.28. The product of those three. So let's use our calculator. And so that's going to be the square root of, and that's going to be 300. Okay, so that's going to be the square root of 300 times parentheses 0.72 close parentheses times open parentheses 0.28 close parentheses there. So the whole thing inside the root, and enter, and there it is. 7.7769, right? Going out to 4 significant values. 7769. Good. Very easy to find, right? Way easier than those complicated formulas from 6.1. So make sure that you recognize when you're working with a binomial random variable, so that if you are asked to find the mean and standard deviations of a binomial random variable, you use these easy shortcut formulas rather than those really ugly complicated ones. Now, unfortunately, if you're asked to find the mean and standard deviation of a random variable that does not satisfy the conditions of a binomial, it's not a binomial random variable, then you're going to have to use those ugly, nasty formulas from 6.1. Okay, so let's see what your author did for these. Okay, so your author gave us the same results. So the mean of the random variable is equal to n times p. which is 300 times 0.2, which is about 216. And the standard deviation of a random variable is NPQ. Remember, this means Q. So 300 times 0.72 times 0.28, square root of the whole thing, gives you approximately this. They just rounded to one decimal, about 7.8. Okay, interpretation. We expect that in a random sample of 300 adult Americans, 216 would rather give up chocolate than their cell phones. Okay, so let's dive a little deeper into this interpretation just to make sure that we have a good idea of what that means. So let's say that we have different groups of people. Let's say we pick one group and it's 300 300 Americans. Right, 300 are in this group. 300 people. And we asked them this question: would you rather give up chocolate or your cell phone? Right, so we get a value of x here. So let's say that in this group, just a nice round number, let's say 200 said, yes, I would rather give up chocolate than my cell phone. Okay, so that's the answer for that one. And then we get another group of 300 people, right? And we ask them the same question. Okay, would you rather give up chocolate? Okay, so in this group, and I'm just making these numbers up just to kind of give you an idea of what the mean represents. So let's say that in this group, maybe 220 people said, yes, I'd rather give up chocolate than my cell phone. So this group said 200, this group said 220. What we want to do is look at the mean of these two. So the mean of these two values is going to be the result of adding them and dividing by 2. So it's 200, zoom out a little bit, is going to be equal to 200 plus 220 divided by 2. That's going to be 420 divided by 2 is going to give you 210. So after two groups, we get a mean of those two groups of 210. So mean including two values is 210. Actually, let me put it over here. The mean with including two values is equal to 210. So now let's say we keep going. We grab another group, a third group, again, 300 people. And let's say that in this group, and again, I'm just making these numbers to make a point. Let's say in this group, 250 said, yes, we would rather give up chocolate than our cell phones. X equals to 250. Okay, so now we have to think about this running total. So now X bar with 3 people would be equal to 200 plus 220 plus 250 divided by 3. Okay, so let's use our calculator now. That would be 200 plus 220 plus 250. That's equals to 670, and divide that by 3. You get 223, approximately 223. So the mean, including 3 people, is 223.3. Okay, and then we keep going. Okay, let's do another one. So now we go back over here, and let's say we grab another group, another randomly selected group of 300 people. Again, we asked them, would you rather give up chocolate or your cell phone? And then this is going to have some other value of X. Well, maybe this one's a little low. Maybe this one's only 180 people said, yes, I'd rather give up chocolate than my cell phone. So then again, we come back over here and we look at the running average, the running mean of these values. So with 4 people included, this would be equal to, oh, this is an equal sign, this would be equal to 200 plus 220 plus 250 plus 180. And now divide that by 4. So let's use our calculator. That's equal to 200 plus 220 plus 250 plus 180. Right? That gives us an answer of 850, and then we divide that by 4 to give us about 212.5. 212.5. So with four people, we get 212.5. 212.5. Okay, well, you get the idea. We keep going. Maybe we have a fifth group. Maybe we have a sixth group. Maybe we have a seventh group, right? So we keep going, going, going until there's a large number of groups. Large, whatever that means. Maybe there's 100, maybe there's 1,000, a large number of groups. And all the while, we keep track of the running mean of those values, right? Every one of these is going to have a separate value of x. This fifth group, 300 people, maybe x is equal to 205. The next group, I don't know, maybe this time it's 138, right? So there's an element of luck and chance that happens with each individual group, but in the long run, there's predictability, right? Statistics always has short-term unpredictability, right? Because there's randomness that happens, but in the long run, there's predictability in the long run. Okay, so if we keep track of this running average, this running mean that will occur as this keeps going for a very large value, so we keep track of this mean for a very large number of samples, right? With 2 samples, with 3 samples, with 4 samples. Now we want to go for the large number of samples, hundreds, thousands, that eventually this number will get really, really, really close. It'll approach 216, right? That's what this is. The mean of our random variable x being 216, it means that eventually these values will get infinitely close to 216. And that's what we call the expected value. Right? So the expected value is equal to the value of our random variable, which in this case is equal to 216. And that means that if we just get one group, anything can happen with one group, maybe 200, maybe 180, right? Anything can happen with one group. But if we get lots of groups, many groups, over the long run, as these number of groups gets really, really large, then the running mean of all those values is going to be 216. So we loosely interpret that to being that it's the expected value. Right? So we expect that in the long run, when we sample 300 adult Americans, about 216 would rather give up chocolate than cell phone. Right? So this is a more technical interpretation of what the expected value represents. But then over here, we kind of condense it into a more simple statement of how to interpret that. On the other hand, the standard deviation, the 7.8, is a measure of how much variability there is in these values. So, for instance, group 1 was 200, group 2 was 220, group 3 was 250, and so on and so forth. But we can easily see that maybe if there's more variability, that these values jump around all over the place. Maybe the first one, we can look at another situation where maybe the first one was really low, 38 people out of 300. The second one was really big, 283 people. The next one was maybe really low, maybe only 17. The next one after that was again really big, 294. Right? So you see with these red ones how there's just a lot of variability. They jump around everywhere. There's less consistency in our values. We might end up with the same mean, right? If we find the running mean of all these red values, they might end up with the same mean, but there's a lot more variability there, right? So the standard deviation would be bigger if these were the outcomes. So that's what this standard deviation tells us. It's an indication of how consistent these values are going to be from group to group to group. The smaller it is, the more consistent those values are going to be. Whereas the bigger it is, the more variability there's going to be. Okay, objective number 4, graphing binomial probability distributions. So let's take a look at this example. Okay, so graph the binomial probability distribution with n equals to 10, p equals to 0.2, comment on the shape of the distribution. So in order for us to be able to graph it, well, we need to know what values we're going to graph, right? So if n equals to 10 and p equals to 0.2, let's create the table that's going to have the values that we need to graph. So we're going to have this big table where the random variable x can take on the values starting at 0 all the way up to 10. So let's just do a couple of them. So then x equals to 0, for example, and the probability that x equals to 0, just to do a quick recap then, would be our formula. Using our formula would be 10, combination of 10, choose 0. Probability of success is 0.2 to the power of 0 times the probability of failure, which would be its complement, 0.8 to the power of 10, right? Because n equals to 10. And then we know now that that is actually the same thing as doing binom PDF of 10, 0.2, 0. Right? This will give us the same answer on our calculator. Then x equals to 1 is the next one. So what's the probability that x equals to 1? Well, that's going to be combinations of 10, choose 1, 0.20 to the power of 1, 1 success, 0.80 to the power of 9, 9 failures, which is going to be the same thing as binom PDF of 10, 0.2, 1. Good. Okay, so let's do a couple more. X equals to 2 is going to be probability that x equals to 1. Oh, sorry. X equals to 2, which is equal to 10, choose 2, 0.20 to the power of 2, 0.80 to the power of 8, which then becomes binom PDF of 10, 0.2, 2. And then we can keep going, right? So dot, 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 all the way out to the very last one. So same pattern, keep going, keep going, keep going, all the way out to x equals to 10. This last one, x equals to 10, is equal to combinations of 10, choose 10, of 0.20 to the power of 10, 0.80 to the power of 0, right? 10 successes, 0 fails. And this is going to be binom PDF of 10, 0.20, or just 0.2, 10. Right? This will give us the same answer right there. Okay, well, let's type in a couple of these into our calculator, get the results. So for this first one, we have distributions, binom PDF, and it's going to be 10 trials. Its probability of success is 0.2. And for the first one, we want the value of 0. So we get an answer of 0.1073. 1074. 0.1074. Right? There's a little bit more than a 10% chance that we'll get 0 out of 10. Okay, so now let's move on to the next one. So this would be distributions, binom PDF. Gives you 10 is the number of trials. Probability of success is still 0.2. And the x value, we're going to put a 1 there. And so now we find the probability that x equals to 1 equals to 2684. 0.2684. Just do a couple more, and we'll just jump to the whole answer. So now we do the same thing, distribution,
binomial PDF, enter. 10 trials, probability of success is still 0.2. And now the value of x is equal to 2. Paste. So binomial PDF 10, comma 0.2, comma 2. Enter. And now that's going to be about 30.1, 0.302 approximately. Okay, let's jump to this last one down here. And let's see what that one is. It's going to be distributions, binomial PDF, 10.2, and then here this becomes a 10. Paste, enter. And now remember, this is scientific notation. It's going to be a very small number. We got to move this decimal space to the left 7 times, which means that we're going to have 6 zeros between the decimal and the first value of 1, which becomes 1024. 1024. So this is going to be 0.12345 1024. 1, 2, 3, 4, 5, 6 zeros. So we move the decimal space to the left 7 times. So a very, very small number. You'll see that our author just approximates that to be 0. Once we get past a certain number here, they just kind of stop detecting it and just put a 0 in there. Okay, but we have an even better way of solving this with our calculator. To create this table, let's do the following. Let's go over to statistics. You're going to hit edit, enter, and then let's go over to list 1, go up, highlight L1, hit clear and enter, and then we're going to need L2 as well, hit clear and enter. If you don't have L1 and L2, then you need to go to stat and then go to setup editor, hit enter again, it'll say done, and then when you go back, you'll see that L1 and L2 are back. Okay, so now we need to type in the values. We're going to recreate this table from 0 all the way out to 10. I'm not going to skip anything now. So we just type in 0, 1, 2, 3, 4, 5, 6, 7, 8, 9, and 10. Okay, so it's a countdown from 0 all the way up to 10. Don't forget to include the 0. And now let's go back up to the top. We're going to go over to the right and then up. Make sure that you're highlighting the L2, make that dark. And then here we're going to type in the function for PDS. So once you're already in the L2, you're going to type in distribution, go down to binomial PDF, hit enter, and then it's 10, number of childs, probability of success is 0.2, and this is what's different. We're not going to type in an individual number. Instead, we're going to hit delete that, and we're going to type in L1. We're going to ask it to go to L1 and type in the individual values that were in our original list. So hit paste, and you'll see the formula is right here, 10 binomial PDF of 10, comma 0.2, comma L1, where L1 is going to be each one of these. So it's going to go through and plug in a 0 and give a value there. And then I'm going to put a 1 for L1 and then put it in there. So hit enter, and you see it automatically populates the whole table. The first value matches this one. And the second value, right, if you want a more specific answer, you can use these arrows to highlight it. The second one on our table is this one. And the third one is this one. And if we had kept going, we'd see we get all the other ones. So this is a nice way of getting all the values right here in the little table in our calculator. Once we have them here in this little table in our calculator, we can use these results to come up with a graph to describe these values. To do that, we're going to go, first of all, hit y equals. Make sure that there's nothing there. See, right now I have an equation in there. Let's hit clear. Let's delete that. You can go down, make sure there's no other hidden equations down there. So no equations. Next, we're going to go to stat plot. So second, stat plot. That's this one. And here we see a menu that describes what's happening to our plots. There are several plots here, and they're all off. That's what this says, off, 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 and that's fine. We get 3 plots, and all 3 of them are off. That's what we want. Okay, so hit enter on the first one, enter. And from this menu, we had some options for plot 1. So we can turn it on by hitting enter again, and then we can highlight off. We want to turn it off again, so we can turn it on and off that way. Likewise, going back to the main menu, let's go back to this one. If one of the other ones was on, so say plot 2 was on, you can go down here and turn it off, right? Because we only want one plot right now. So make sure that the other ones are off. If this one is on, then you would go in here and select off. Okay, so go back to stat plot, hit enter, select on. We do want it to be on. Go down by 1, and then you get to choose what kind of graph you want to do. So we've used this before. We created box plots before. We've created histograms before. So now we want to use it to create these bar graphs here. So hit enter. And then we want to go down, and we want to select the X list to be L1. That's where you put the values of 0, 1, 2, 3, 4, 5, 6. And then we want the height of each one. So these are going to be the x-axis values, are going to be the values on list 1. And we want the y-axis values to be the frequency, and that's going to be the values that are on list 2. These are the probabilities associated with each value. So we're going to hit L2 right here. Good. That's assuming that you put your values on L1 and L2. If you put them on different lists, just keep track of that and put them here. Okay, so now that we have that, if you have the newer ones, then you can choose colors and stuff, but the older models don't have a color, and that's okay. Next, we're going to go over to where it says window, and we're going to choose a nice window for our graph. We ranged from 0 through 10, so let's go from -1 through 11. That'll guarantee that we have the numbers we want from 0 through 10. Okay. The scale, we want it to be a 1 because we want it to go in multiples of 1. If you choose 5 here, it would go 0, 5, 10, 15, 20. We don't want that. We want each one to be a width of 1. And then for the y-axis, we're starting at 0. The lowest value you can get is a 0. And we're going up to a maximum of 1 for sure, right? 1 to 100%. However, we can always come back and adjust this because the highest value might be this 30%, 0.3. So if the highest value is about a 0.3 or 0.4, you'll see that it doesn't really give us the best picture. We can always come back and adjust that. Okay, so now we hit graph, and this is what we get. So we get a little bar graph that describes that table. If we hit trace, then we see some information here. Forget that one because it's -1, right? So I just put it there to capture that far left value. But if we go over, we see that when we get a 0 value, we get this, 0.10, right? 0.10. Then if we go to the right, we see that when we get a 1, that's a 0.26. That's this guy right there. And then when x equals to 3, I'm sorry, when x equals to 2, and so on and so forth. Notice that these ones way over here are so small that they don't really register. They're really, really tiny. But if we use the trace button, then we can get that value. So we can go over here to 10. We see this value right here is right there. 1.024 times 10 to the -7 is that value right there. But also notice this ginormous empty space here, right? A lot of white space there. And that's because the tallest one, the biggest value, was only a 0.3, it was this one, 0.32. So we can come back over here to our window and then change the maximum y value, right? So based on that, I know that 0.35 should be more than enough to capture the tallest rectangle. Hit graph. Now it looks a little nicer. Right? We just kind of zoomed into it a little bit and we can kind of get a better sense. Still, these are so small they don't even register, but we have a pretty good idea. Right? So then you can use this to come up with a graph that represents the probability distribution table. Okay, let me adjust this a little bit over here. Okay, so the value of this picture is that we get to see a sense of the overall picture of what's happening, without necessarily focusing on the individual values. From here we can see that When x is a small value like 0, 0, 1, 2, 3, there's very high likelihood that we get results in that area. And then they taper off after that, and then they're just so small over here that almost not detectable. And so we can also see kind of the shape of this, the shape of the graph. It seems almost bell-shaped, except it's heavily skewed in one direction. Is that hopefully you can see that. Let's take a picture of this and then change the values. So this is that first one. Okay, now let's go back over here and change it. So instead of, let's go back to our stat, edit, and let's come back up here. Let me change this to a third one. Clear, enter. I'm going to go to L3, and I'm going to come up with a new, I'm going to do a new graph when P equals to a different value. Let's say P equals to, so distribution, we'll keep 10 trials, but let's say that P equals to 0.7, 0.7. And then we're still going to leave the x values as S1, L1, hit paste, enter. So these are now the reported probabilities when P equals to 0.7. Good, 0.7. Okay, so now let's graph this one. So let's go back to stat plot and let's go into plot 2. Let's turn it on. We'll leave it in red. And it's going to be these guys. And it's going to be L1. And then this time we want L3. So we'll graph it in red. Graph. And there we go. Okay, so the blue one was when we had 0.2 probability. And you see how it's kind of skewed in this direction. The most likely outcomes when we have 10 are going to be about 3, right? And then 0, 1, 2, and 3 are very, very common. Sorry, I said 3. 2 is the most likely. 0, 1, 2 is the most common one. And then if we change P equal to 7, then these are more likely over here. Right? So we can get a sense. Still, we have this kind of a mountain shape, a bit of a bell shape. It's just that it's skewed either in this direction or this direction. Good. Skewed left is the red one. Skewed right is the blue one. The most likely outcomes are kind of bigger numbers now when P equals to 0.7. And now let's do one last one. Edit, to the right, go up. Let's do one last one. Stat, distribution. Let's go to Binomial, PDF. And now let's say that it's exactly 0.5, 0.5, L1, paste, enter. So now we have those values. And now let's go to our stat plot. And let's go to plot 3, enter, down. We want to pick this guy, enter. There we go. L1, L4, green, graph. There they are. Okay, it's kind of a mess, but we can hopefully identify. The blue is when P was equal to 0.2. The red ones, that's when P equals to 0.7, whereas the green ones are when P equals to 0.5. Okay, you know what? Maybe I should just turn them off and do them one at a time. So let's go back to, so a shortcut, you can come up here to y equals, see how all 3 of these are dark. If we go up and select enter and move away, now it's no longer dark. That means plot 1 has been turned off. And if we go over here and select this, enter, move away, now plot 2 has been turned off. So only plot 1, I'm sorry, plot 3 is the only one that's active now. So we hit graph, now we see just the green one. Okay, so if we look at just the green one, we see that this does look like a closer to a bell-shaped distribution, centered right in the middle, right in the center of this distribution. So it's nice and symmetric. That's one of the patterns we'll notice, that as p gets closer to 0.5, that the distribution will start to look more and more like a nice bell shape, and that is improved as n goes higher. So for example, let's redo this with a higher value of n. All right, so let's go back to stat, edit, and let's pick a larger value of n. So let's go back down to this guy, a little bit limited by how many spaces we can have here. This is 11. Okay, so I went all the way down to 30. So I have counting from 0 all the way up to 30. Make sure I didn't skip anything. Okay. All right, so now I'm going to come back over here, and I'm going to use L5 now. Clear, enter, go up to L5. You're going to hit distributions, PDF, Binomial PDF, hit enter. And now there's 30 trials. 30 trials. Probably success. Let's leave it as 0.5. And I'm referencing L1. Paste. Enter. Okay, so now I have all those values. This gives me all those probabilities associated with each value. And now let's graph L5. So let's go to stat plot. And let's redo 3. And let's just change this to L5 now. And let's change the color. Brown. Let's go with orange. Graph. Oh, so we need to change our window, right? This only goes from 0 to 10, and we're going to 30 now. So we got to change our window, and let's make it to 31, and graph, and there. Right, so from 0 all the way out to 31. If we wanted to know a specific value here, we can hit trace, and then this will let us know. We can go to the right and keep track. So this is when, let's move over here, when x equals to 10, the probability turns out to be pretty small still, 0.027. And when you go up, see like the most common result, the tallest value is 14. Well, now that we know that the tallest one is 14, we can also come back to our window and change this and maybe make it a little bit closer. How about 0.15? And then hit graph, and now we see that there it is. The tallest one is right there. And we see that it's starting to look an awful lot like a nice smooth bell shape, right? The bigger that n gets, the closer to a smooth bell shape that we will get. Okay, so that should hopefully be enough to tackle your homework questions.